the screen?
Yes.
Okay, great. Well, we'll go ahead and get going then, and we'll pick up where Chance left off yesterday, about halfway through chapter 5. So as Chance probably mentioned to you in the first part of chapter 5, if you have a background in concrete mix design, then a lot of this information will be kind of basic for you. This is an introduction to concrete mix designs. We don't get too deeply into the weeds. If you do not have a background in concrete mix design, then you may, I'm not sure what kind of expectations you had coming into this class, but hopefully this chapter will give you a good introduction to concrete mix design development. One thing that you probably already picked up on in the previous example mix design that Chance did with you yesterday is that concrete mix design development is as much art as it is science. The guidelines that we use in developing concrete mix designs are really just intended to get us close to where we want to be with the material properties of our mix design. They're not really intended to give us a fine-tuned mix design. The process of getting the design to the point where it's really useful to us comes through the trial batching process. So as we go through this example, we're going to do another example today. As we go through that example, there's going to be instances where we say, based on experience of the technician, we're going to go ahead and make this assumption or go ahead and make this change. So all of that may seem kind of arbitrary to you if you don't have a background in concrete mix design development, but that is the reality of mix design. The more experience that you have, the easier this process is, the more intuitive the process is. So usually you'll be given whatever information that you need. Like for the exam, you'll be given the specific information that you need in order to answer the questions. But in the real world, concrete mix design development does rely a lot on experience, and oftentimes based on your experience, you can cut corners, you can speed up the process, as opposed to just going step by step through the ACI 211 process, which is what our TM 103 chapter 5 is based on. Okay, so that being said, let's jump into another mix design example. This one is in your book. It starts on page 5.5, bottom of page 5.5. So in this mix design, we have double T's for a parking garage in Podunk, Connecticut. So this mix design is being developed for a application of double T's in a parking garage. The coarse aggregate that we're going to be using has a maximum aggregate size of 3/4 inch. We're targeting a natural slump of 3 to 4 inches. Our fine aggregate specific gravity is 2.65. Coarse aggregate specific gravity is 2.60. The fineness modulus of our fine aggregate is 2.7. The dry rotted weight of our coarse aggregate is 104.7 pounds per cubic foot. We are going to be using some admixtures. We're going to be using a water reducer and a superplasticizer. For stripping strength, we need 4,000 psi, and for 28-day strength, we need 5,000 psi. And then the cover on our reinforcement is at least 1.5 inches. So those are the basic parameters that we're given that we need to develop a mix design around these parameters. So in this example, the first thing that they're going to do is to look at the water cement ratio. So there's a couple of different tables that we look at in determining our water cement ratio. Table 5.4.2 is based on the exposure conditions. So we need to consider exposure conditions. And then table 5.4.3 is based on our strength requirements. So notice that with regard to our strength requirement, we have both a stripping strength and a 28-day strength section of the table. So between these two tables, between 5.4.2 and 5.4.3, we can come away with three different water cement ratios. And so then that raises the question, if we have three different recommended water cement ratios based on these two tables, which of those water cement ratios do we use? Well, the answer is we're going to use the smallest water cement ratio. So in our example, we do have concrete that's going to be exposed to freezing and thawing. So it will need to be air entrained. And so looking at table 5.4.2, we come away with a recommended water cement ratio of 0.45. That's a maximum water cement ratio. So we are talking about double T's. Those are thin sections. Usually the flange of a double T is in the neighborhood of 4 inches. So that would be considered a thin section. It is going to be exposed to freezing and thawing, and so that gives us a recommended water cement ratio of 0.45. And then looking at table 5.4.3, we have a required stripping strength of 4,000 psi, and so based on table 5.4.3, we have a recommended water cement ratio of 0.37, and we also have a 28-day strength requirement of 5,000 psi. And so based on table 5.4.3, we come away with a recommended water cement ratio of 0.40. So between these three water cement ratios, we're going to use the smallest one. So we'll be using 0.37 as we continue with developing this mix design. All right, next let's look at our mixing water. So we go to table 5.4.1. So in this example, our mix is going to be air entrained. So make sure that you are looking at the air entrained section of table 5.4.1. We have a 3/4 inch maximum aggregate and a 3 to 4 inch natural slump. So based on those parameters, we are air entrained. We have a 3 to 4 inch natural slump and a 3/4 inch aggregate. And so we have a target water content of 305 pounds. So based on table 5.4.1, we have a target water value of 305 pounds. All right, now we are going to be using some water reducing and superplasticizing admixtures. And so based on the experience of the technicians who are doing this mix design, they know that when using a water reducer and superplasticizer together, that they can typically reduce the water contents from table 5.4.1 by around 18%. So instead of waiting until later on in the mix design development process, they're just going to go ahead and make that change now. And so that reduces our water content from 305 pounds down to 250 pounds. Also based on table 5.4.1, we have a recommended air content of 5%. That's based on our 3/4 inch aggregate and moderate exposure. So we have a recommended air content of 5%. All right, so at this point we have our water weight, 250 pounds. We have our target water cement ratio, 0.37, and so we can calculate our cement content. So remember, our water cement ratio is, just as the name implies, it's water divided by cement. So if we know the water, we know the water cement ratio, we can calculate the cement by taking the water weight and dividing by the water cement ratio, and that gives us 676 pounds of cement per cubic yard. All right, so at this point we've got our water weight and our cement weight. So next, let's look at our volume of coarse aggregate. So we can look at table 5.4.4. We do have a 3/4 inch aggregate. Our sand has a fineness modulus of 2.70, and so we can go to table 5.4.4 to determine our volume ratio. Now notice that in table 5.4.4, there isn't a column for a fineness modulus of 2.7. There's a column for 2.6 and a column for 2.8. So what we would need to do in that situation is interpolate between those two columns. We're going to be right between those two columns. And so when we do that for a 3/4 inch aggregate, we come up with an interpolated volume ratio of 0.63. All right, so our volume ratio of coarse aggregate is 0.63. So we need to convert that to an actual weight of coarse aggregate, and we do that by multiplying the volume ratio by the dry rotted weight of the aggregate. So 0.63 times 104.7 pounds per cubic foot gives us the amount of aggregate we need per foot, and we multiply that by 27 to get the amount of aggregate we need for a yard. So that gives us a total aggregate weight of 1,781 pounds per cubic yard. Okay, so at this point, we have our water weight, our cement weight, and now our coarse aggregate weight. So next is our fine aggregate. The rest of our volume is going to be filled in with our fine aggregate. So we need to know how much volume we need to fill with that aggregate. And so we determine that volume by calculating the volumes of all of our other materials, water, cement, and coarse aggregate, and then subtracting that from our total volume of 27 cubic feet. All right, so our water volume, we have 250 pounds. The specific gravity of water is 1.0. The unit weight of water is 62.4. So that gives us a volume of 4.01 cubic feet. Next is our cement. We have 676 pounds. We were given that the specific gravity of our cement is 3.15. So that calculates out to a cement volume of 3.44 cubic feet. And then for our coarse aggregate, 1,781 pounds divided by the specific gravity of 2.60 and the unit weight of water gives us a coarse aggregate volume of 10.98 cubic feet. All right, don't forget about the air. You may hear me say that more than once. Even though air does not weigh anything in our calculation, it does take up volume in our mix design, and so we always need to make sure that we account for the air when we are looking at the volume. So we're using 5% air here, so 5% of 27 cubic feet is 1.35 cubic feet. So that's how much air we have in our mix design. So we add up all of these volumes, we get 19.78 cubic feet. Subtract that from 27, and that gives us 7.22 cubic feet, which is the volume of the fine aggregate that we need to use. All right, so at this point we have our water weight, our cement weight, our coarse aggregate weight, and our fine aggregate volume. So we need to convert that fine aggregate volume into a weight that we can use in our batching process. So we're given that the specific gravity of our sand is 2.65. So we can calculate the weight of our aggregate as 1,194 pounds per cubic yard. All right, so now we have the weights for all four of our primary ingredients. So we can add up those weights: 250 pounds of water, 676 pounds of cement, 1,781 pounds of coarse aggregate, 1,194 pounds of fine aggregate. Divide those by 27, and we get a theoretical unit weight of 144.5 pounds per cubic foot. So that's right in line with what we would anticipate our unit weight to be for a regular weight aggregate mix design. This looks to be a good starting point for doing some trial batching to get this mix design dialed in so that it is performing exactly the way we want it to perform for this application of double T's in a parking garage. All right, so let's look at adjusting this mix design for actual moisture contents. So the mix design that we just looked at is based on dry aggregate weights. We were using the dry rotted weight of our coarse aggregate and the dry weight of our fine aggregate. Most of the time we want to have our mix design stated as SSD, aggregate weights, saturated surface dry. So we need to convert our dry aggregate weight mix design to an SSD mix design. So the way that we do that is we take into account the absorption of the coarse aggregate and the fine aggregate. In this case, the coarse aggregate has an absorption of 0.6%, and the fine aggregate has an absorption of 0.4%. So we can convert our mix design to SSD weights by multiplying our dry coarse aggregate weight by 1.006 to account for the 0.6% absorption. And so that gives us an SSD coarse aggregate weight of 1,792 pounds per cubic yard. Same calculation for our fine aggregate using the absorption of 0.4%. Multiply that times our dry weight of 1,194 pounds. And that gives us a target SSD weight of 1,199 pounds per cubic yard. All right, so this is our SSD adjusted mix design. All right, next let's look at adjusting the weights for the actual moisture conditions that are occurring today. So we've gone out, we've done some moisture testing of our aggregate, and we've determined that the coarse aggregate has a total moisture of 1.5%, and the fine aggregate has a total moisture of 5.2%. So we're using a few different terms here that should be familiar to you from level 1 and level 2 with regard to aggregate moisture. In this slide, we're talking about total moisture. In the previous slide, we were talking about absorbed moisture. And so we assume that you already know the relationship between these different moisture conditions. Just as a quick refresher, the total moisture is all of the moisture that's present in the aggregate. The absorbed moisture is the moisture that is confined within the aggregate particle. And so then the free moisture is the moisture that is available to contribute to your mixed water that's on the surface of the aggregate. All right, so in this case, we've got a total moisture of 1.5% for the coarse aggregate and a total moisture of 5.2% for the fine aggregate. So let's adjust our coarse aggregate weight to account for today's conditions. So there's a couple of different ways we can do this. The way they've chosen to do it is to start back with our dry weight and use the total moisture. So our dry weight of coarse aggregate was 1,781. And so we just multiply by that 1 plus the total moisture, 1.015, gives us 1,808 pounds of coarse aggregate per cubic yard. So in this way, we're accounting for both the absorption and the free moisture because we're multiplying by the total moisture. Same calculation for the fine aggregate. We have a total moisture of 5.2%, and so that calculates out to 1,256 pounds per cubic yard of sand. All right, so what's the free moisture? How much of the aggregate batch weight is actually water that is contributing to the water cement ratio? So we can determine that by looking at our batch aggregate weight and subtracting our SSD aggregate weight. So in this case, our moisture adjusted coarse aggregate weight is 1,808 pounds. The SSD weight is 1,792 pounds. And so that gives us a difference of 16 pounds, which means that we're getting approximately 2 gallons of water into our mix by way of the coarse aggregate, the free moisture in the coarse aggregate. All right, same calculation with our fine aggregate. Our moisture adjusted batching today is 1,256 pounds. Our SSD weight is 1,199 pounds for a difference of 57 pounds per cubic yard. So that means we're getting 57 pounds of water into our mix by way of the fine aggregate. All right, next let's look at some trial batching. So we're going to do a trial batch. After we did our testing of that trial batch, we have some data that we need to take into consideration. The first piece is that the mix was harsh, meaning that it really didn't have the workability that we had anticipated it would have. It only had a slump of 1.5 inches instead of the 3 to 4 inch slump, natural slump that we had anticipated. So what we're going to do to account for this is we're going to add some water to raise the slump. But if we add water, we want to maintain our water cement ratio, so that means we need to increase our cement content as well. All right, so if we add water as part of our trial batching process, then we need to add cement as well so that we are maintaining our water cement ratio. If we're adding material, then that means material has to be taken away. So we're going to have to adjust our coarse and fine aggregate weights accordingly. Once we've gone through this process, we would then batch a new trial batch and evaluate whether or not that these adjustments that we've made are helping the mix to be closer to what we would anticipate and what we need that mix to be. So generally, we're going to go through the trial batching process more than one time. We're going to keep making small refinements to our mix design with each trial batching session until we have that mix dialed in so that it is performing the way that we need it to perform. All right, so here is the real work in developing our mix design is during the trial batching process, seeing how the mix performs, and then based on that performance, making adjustments to the mix to refine the performance so that it is meeting the specified requirements for our particular application. Right, there's a topic in your book on page 5.9. There's a section there on optimum sand percentage. Basically what the optimum sand percentage is the ratio of sand to coarse aggregate that allows us to use the minimum amount of cement in our mix design. So this is a way of economizing the mix design, and we can't usually just calculate the optimum sand percentage. Usually we have to do some trial batching. We have to make some adjustments to our sand percentage and plot the results of that sand percentage and the amount of cement that we're using and the strength to determine at what point we have that optimum sand percentage. But I draw your attention to this just as just so you're aware that there are some ways that we can go about economizing our mix. There are other ways that we have either already talked about or will talk about in the class, but this is one of those tools that you have in economizing a mix design as part of the mix design development process, and that is determining the optimum sand percentage, which typically is going to give you the least amount or minimum amount of cement that's needed in the mix in order for the mix to achieve the desired strength performance. All right, next let's talk about adjusting a mix for silica fume or microsilica. Generally, if we're going to use silica fume, it's for one of two reasons. Sometimes a project specification will say explicitly that microsilica must be used and may give the amount of silica fume that is required as a percentage of the cement weight. But there are other times that silica fume may not even be mentioned in the specification, but there are performance requirements for the mix design that in order for us to meet those performance requirements, we have to use silica fume. Okay, so that's two different ways that we may come to the point of using silica fume. Either it's specified for the project or the project has performance requirements that necessitate us to use silica fume. Generally, we're going to state the amount of silica fume to be used as a percentage of the cement. Unlike how we would use a pozzolan such as fly ash, where we're using fly ash as a replacement for a portion of the cement, with Silica fume, typically we are not replacing a portion of the cement, we're adding the silica fume to the cement. So it's in addition to the amount of cement that we've already determined. If we are going to be batching the silica fume as an emulsion suspended in water, then we need to know specifically what proportion of that emulsion is silica fume and what proportion is water, so that we can account for that water in our batching of additional water into the mix. Right? If we don't account for the water in the emulsion, then we're going to be over batching our water, raising our water cement ratio, and hurting ourselves with regard to the strength, performance, and durability of the mix. All right, since we're adding a material here by adding silica fume, that means we need to take some other material out. I've already said that typically when using silica fume, we're not going to take out cement. So the next finest material would be the sand. So however much silica fume we use in the mix, we need to take out a corresponding volume of silica fume, or of sand rather. So keep that in mind. We're not replacing the sand pound for pound. We're replacing the sand cubic inch by cubic inch. All right, so since the specific gravity of the silica fume is different than the specific gravity of our sand, then that means we will be taking a certain weight of sand out, but adding a different weight of silica fume so that the volumes are the same. As we discussed on Monday, anytime we're using silica fume, it does have some adverse effects on our mix, and that the mix tends to not have as much workability. It tends to not have as much bleed water. And so for that reason, if we adjust a mix to incorporate silica fume, more than likely we're going to have to either add superplasticizer, or if the mix is already superplasticized, we're going to have to adjust that superplasticizer dosage up so that we can achieve the desired workability for our silica fume mix. All right, next is design of lightweight concrete mixes. There's a good discussion in your book with regard to lightweight concrete mixes. There are tables at the end of the book after the tables that we've already been looking at that are intended to be used when developing a lightweight concrete mix design. There are several different reasons why we may want to consider a lightweight concrete mix design. Oftentimes, lightweight concrete is more expensive than regular weight concrete. So the advantages of using the lightweight mix design have to economically outweigh the disadvantage of the added cost of the material itself. So there are a couple of advantages to using a lightweight concrete mix design. One is shipping costs and erecting costs. So lightweight concrete mixes that are used in precast design are typically sand lightweight or semi-lightweight mixes that are in the neighborhood of around 120 pounds per cubic foot. We can have concrete that has a lower unit weight by using all lightweight sand and coarse aggregate. We could get down into the range of 90 pounds per cubic foot. But typically what we see used in precast plants is regular weight sand and a lightweight coarse aggregate. And usually those mixed designs have a fresh concrete unit weight somewhere in the neighborhood of 120 pounds per cubic foot. At one plant it might be 115, at another plant it might be 125. But on average over the years, what I've found is 120 is a good working assumption for the unit weight for a semi-lightweight concrete mix. So by using a lightweight mix, we can reduce the weight of our precast units, which may help to save money on shipping costs as well as crane costs during erecting. Cranes are expensive, and generally the cost of the crane is directly related to the capacity of the crane. So a higher capacity crane generally costs more than a lower capacity crane. So if by using a lightweight concrete mix design, we can get away with using a lower capacity crane on the job site, then that could be a significant amount of savings in the erecting process. So that's one reason why we might want to use a lightweight concrete mix design. Another reason is that the weight of the structure is directly related to the seismic load on the structure in high seismic regions. And so if we can lower the weight of the structure by using lightweight concrete, then we are lowering the seismic load on the structure that may result from an earthquake, which can help to simplify the framing, the other structure of the building. So that's another reason why we may want to consider using a lightweight concrete mix design. The big problem with using a lightweight aggregate is the high absorption of that aggregate. Whereas with a normal weight aggregate, we may be looking at a 1 to 2% absorption, or even less than 1%. But for a lightweight aggregate, we may be looking at an absorption of 25 to 30%. So significantly more absorptive than a regular weight aggregate. That wide variation in moisture conditions that can occur in the lightweight aggregate really complicate the batching and mixing process. And so for that reason, using lightweight aggregate is more difficult with regard to the batching process than using a regular weight aggregate. Most plants that use lightweight aggregate, they take some additional steps to help ensure a more consistent moisture condition. One thing that they can do is to cover their aggregate stockpile so that it is out of the rain, it's out of the sun. That helps to keep the moisture content more consistent. Oftentimes they also sprinkle the aggregate, keep water running on the aggregate at all times so that they're maintaining a consistent level of moisture in the aggregate. Even with taking these steps, there's going to be some variation in the moisture condition of the aggregate, not just from day to day, but also from batch to batch. And so very tight controls on batching need to be employed to ensure that we get a consistent mix from one batch to the next. All right, just like with regular weight concrete mix design, the real work in dialing in the mix comes through the trial batching process. If the tables for the regular weight mix design got us just in the neighborhood of where we need to be, then the tables for the lightweight mix design just maybe get us into the county that we need to be. They're less precise than the other tables that we've been looking at, and so there is a lot more work to be done during the trial batching process with the lightweight mix design than even with a regular weight mix design. So for that reason, what I generally recommend to people is that instead of following the steps in your TM103 for lightweight concrete mix design development that come from ACI 211.2, there's nothing wrong with going through that process. You can certainly do it that way, and the tables are provided, the references are provided. But I think a better way to approach a lightweight concrete mix design development is to determine who your lightweight aggregate supplier is going to be, and then talk to your sales rep at the aggregate supplier and give them the parameters of the mix design that you need as far as what product the concrete is going to be used in, what kind of strength that you need, both for stripping and 28-day from the concrete, what kind of workability you're going to need, and ask the sales rep to provide you with a template mix design. So the aggregate supplier should have a lot of information regarding mix designs that their aggregate has been used in. And so oftentimes they can give you a starting point mix design that will be just as good, if not better, than the starting point mix design that you would develop on your own using the tables from MNL 103 and ACI 211.2. Okay, so it's a lot quicker just to get a template mix design from your aggregate supplier and it takes a lot less time on your part. And oftentimes that is a better starting point than going through the development process would be. But once you have that mix design from the aggregate supplier, trial batching is still going to play a pivotal role in your mix design development process. It's unlikely that they will be able to provide you with a mix design that is exactly what you need. More than likely, you're going to need to tweak that mix design to some extent, either with regard to the cement content to dial in the strength so that it's not overperforming or underperforming on strength, or maybe you need to make some other adjustments to modify the workability of the mix. Either way, trial batching is the tool that should be used in that process. And after a few rounds of trial batching using a supplier's template mix design, you should be in pretty good shape with your lightweight concrete mix design. So that's the recommendation. Instead of going through the tables in the book, you can do that. That works. But in real practice, getting a trial mix design from your aggregate supplier is probably the best first step. All right, so looking at the process in your book, again, all the tables in the book come from ACI 211.2. ACI 211 and 211.2 are updated on a fairly regular basis as more information is made available, as more research is done with regard to concrete mix designs. The ACI methods are updated accordingly. So always go to the most current version of ACI 211.1 and 211.2 if you are going to use the tables and the guidance from ACI 211 in developing your mix design. So the basic steps for a lightweight mix design from ACI 211.2 is you're going to start by selecting a target slump range where you want to be. You should know the size of your lightweight aggregate because you will need to select an aggregate supplier prior to going through this process. Depending on what part of the country you're in, you may have several different suppliers that you can choose from, or you may be very limited and there may only be one viable supplier to your particular area. So once we've gone through selecting our slump and the size of our lightweight aggregate, next we need to look at our air content. Air content can be established either based on the project specification or by using the tables from ACI 211.2. Either way, we need to establish our target air content at this point, and then next we're going to look at our cement weight. Now notice, looking at figure 5.4.2, for a lightweight mix design and getting our target cement weight, it's more of a I'm sorry, figure 5.4.2. If I said table 5.4.2, I'm sorry. It's figure 5.4.2. You can see that this just provides a band of target in the target range. So it's not very specific at all based on your cement content and your compressive strength requirement. It gives you a pretty broad range that you could choose from. So again, the process, the 211.2 process for a lightweight mix design is even less precise than the process that we've been talking about for a regular weight aggregate mix design. All right, after we've got the cement weight, next would be our aggregate content. That's going to be based on the volume. This is where a lightweight concrete mix design gets a little tricky because the weight of the aggregate can vary widely based on the moisture content. So we really need to base the aggregate on the desired volume and make sure that we're making precise adjustments for the actual moisture content on a day-to-day basis. If we're not accurately adjusting a lightweight mix design for the moisture content, then the yield of our mix can vary significantly. So usually if for a lightweight mix design you're having issues with yield, probably one of the first things that you should look at is how you are accounting for the aggregate moisture. And if you are accurately accounting for the aggregate moisture, then you shouldn't have any issues with wide variations in the yield of the mix. All right, and then lastly is our water content, and then we start the trial batching process. So that's the basic steps for developing a lightweight concrete mix design. All right, as far as control of lightweight mixes, we have to make frequent checks of the fresh concrete unit weight. That's another indicator of how accurately we are accounting for the aggregate moisture. If we're not accurately accounting for moisture, then we're going to see variations in our fresh concrete unit weight. The unit weight shouldn't vary more than plus or minus 2% from test to test. So from whatever the target unit weight is based on our mix design, the actual unit weight should be within plus or minus 2% of that target's unit weight. As far as controlling the aggregate moisture, we've already talked a little bit about storage methods for lightweight aggregate. So we keep coming back to this issue of variation in moisture in the lightweight aggregate because really all of the issues that surround using lightweight concrete generally are derived from controlling the aggregate moisture or accurately accounting for the aggregate moisture. So we really can't overstate how important it is that you properly evaluate the coarse aggregate, the lightweight coarse aggregate, on not just a day-to-day basis, but on an hour-to-hour or sometimes even minute-to-minute basis to ensure that the aggregate moisture is being properly accounted for in the batching process. Using a moisture probe on your lightweight aggregate bin is very helpful, where the probe is monitoring the real-time moisture content of the aggregate as it's being discharged from the bin onto the weigh belt. So that will generally help in controlling the batching of a lightweight mix such that your yield is consistent and the unit weight is consistent, but many plants are not equipped with a moisture probe on their lightweight aggregate bin, and so that definitely complicates the batching process. All right, that is it for lightweight concrete. Next is design of architectural concrete mixes. So this is page 5.17 in your manual. So generally when we start designing an architectural concrete mix, we're starting from a different perspective than we would a structural mix. So up to this point, most of the things that we've really been focused on are the performance of the mix. We've talked about air content, we've talked about workability, we've talked about strength. All of those things up to this point have been the primary drivers for developing our concrete mix design. But with an architectural mix design, that is not the case. The primary driver of our architectural mix design is going to be the appearance of the mix, the aesthetic qualities of the mix. And so in order to determine what those aesthetic qualities are, generally we're going to establish some design criteria that revolves around finished samples. So we're going to develop some finished samples based on the preliminary information that we have from the architect. That information may be referenced to another project that will give us an idea of what kind of color and texture the architect is interested in. There are also sample color and texture books that architects can refer to and that then the plant can refer to see what the architect has envisioned for this particular project. So the first thing we're going to do is some finished samples to send to the architect so that we can kind of get the appearance of the mix design dialed in. And once we've done that, then we'll start worrying about the mix strength and the workability of the mix and the air content and those other more technical aspects. But the first thing, the most important thing for an architectural concrete mix design is the appearance, the aesthetic qualities. So when we send finished samples to the architect for review, initially we may just be looking for confirmation of what exactly the architect has in mind. So once we've dialed that in, we know what color the architect is looking for, what kind of etch the architect is wanting. Then we can really get to the hard work of developing our mix design and really fine-tuning the appearance of that concrete so that it is exactly what the architect is wanting. So once we've gotten to that point, we're still going to be exchanging finished samples with the architect, getting approval. The last thing that we want to do is submit a perfect finished sample because that is what the architect is going to expect all of the panels to look like. So generally what we want to do is establish a reasonable range of variation. And so for that reason, the plant may want to submit 3 samples. One sample showing, that perfect finish. This is what, on a perfect day, this is what it's going to look like. Another sample that shows, it's not going to look any worse than this. If it looks any worse than this, then, we're going to fix it or we're going to scrap it, we're going to remake it. And then a third sample that's in between those two that gives the architect an idea of day in, day out, this is what the panels are actually going to look like. All right, so in establishing that appearance approval, we don't want to just send a perfect finished sample because then we may be putting ourselves in the position that the owner is then going to expect all of the panels to look perfect. That's not realistic. Each plant has their own range of variation based on their capabilities, but there's going to be some variation from any plant. And so we want to accurately capture that acceptable variation in our finished samples so that the architect has a clear understanding of what that variation is going to be and can then give approval. All right, so once we've got approval for the appearance of the mix design, then we need to shift gears and we need to start looking at, okay, how do we achieve the required strength performance out of this mix? How do we achieve the desired workability? We may be using a gap graded aggregate in order to achieve the desired appearance. A gap graded aggregate can give us decent strength, but it may adversely affect the workability of our mix. So we may have to use some different admixtures to account for that loss of workability in using a gap graded aggregate. So all of these things need to be taken into consideration, but they come secondary to establishing a mix design that has the appropriate appearance that the architect is looking for. All right, there's a section there talking about aggregate size. Usually the size of aggregate that we select for an architectural mix design will depend on the type of finish that is going to be applied. If it's going to be a light sandblast or an acid etch, where the coarse aggregate is not really exposed and very little of the fine aggregate is exposed, then the aggregate size that's being used is not as critical. We're more than likely going to be able to use an aggregate that meets ASTM C33 gradation requirements, that has a good uniform gradation curve. But if we are going to be producing this mix for panels that has a retarded finish or a heavy sandblast finish or a very heavy acid etch finish where our coarse aggregate is going to be exposed and certainly our fine aggregate is going to be exposed, then the aggregate size is going to be more critical. Selecting the appropriate aggregate size is going to be more critical in achieving the desired appearance and aesthetics of the mix. So we need to keep that in mind during our initial process of developing finishes for approval, we need to be selecting aggregates that will contribute to the desired appearance as opposed to detracting from that desired appearance. Okay, trial batching is still important with architectural concrete mixes. Once we've got the appearance dialed in, we may have to do some trial batching to make sure that we're meeting all of our other performance parameters, and at the same time comparing those trial batches aesthetically to each other to make sure that we're not doing anything that that detracts from the finished sample that has been approved by the architect. All right, sometimes with architectural production, we use two different mixes in a panel. Architectural face mixes tend to be more expensive than regular structural mixes. So in order to economize the cost of a project, we may use the architectural face mix for the couple of inches that are the face of the panel, and then fill the remainder of the panel with a structural mix. This is very common in architectural precast. If you've got a 6-inch panel, then do 2 inches of architectural face mix and 4 inches of gray concrete. That saves a little bit of cost, but still gives us the same appearance that the owner is looking for. So one thing to keep in mind when using two different mixes in combination with each other is that those mixes need to be compatible. They need to be similar in design. If our face mix has a significantly different water cement ratio than the backing mix, or significantly different aggregate sizes between the two mixes, then over time this can cause a problem in the panel because those two mixes may expand and contract with thermal and moisture changes differently, which could cause the panel to bow or even to crack or delaminate. So generally we want to use similar proportions between our face mix and our backing mix just to help minimize those potential issues. Another thing to keep in mind with architectural mix design is that it's a good idea to keep those finished samples that have been developed, keep them around the plant because they may come in handy in the future. You may have an architect who's doing a new project, and you may already have a mix design that's been developed that is exactly what the architect is looking for. So if you've got finished samples on hand, then you can show those to the architect, and if they're exactly what he's looking for, then great, you've already got your mix design developed. If they're not exactly what the architect is looking for, but they're close, then that gives you a really good starting point for developing the mix design for this new project. The mix design does need to be approved prior to going into production. If you go into production with an architectural mix design that has not been approved, then there are risks associated with that. There's also absorption testing that needs to be done for architectural face mixes. That absorption testing needs to be completed before the mix goes into production because there are limitations on how much absorption is acceptable. An architectural face mix should have an absorption of 6% or less. So it's important that we conduct our absorption testing before going into production so that we've confirmed that we're meeting that PCI requirement. All right, that is it for Chapter 5. Do we have any questions on Chapter 5?
We haven't had any questions come in.
Okay. Well, certainly if you have questions as we go along, either type those in or I'll try to remember to stop periodically and ask if anybody has questions. But seeing no questions at this point, we'll go ahead and continue on with Chapter 6. I'll probably not spend as much. Okay, go ahead.
One question just popped in. When doing an architectural mix, do we add pigment to the weight or volume?
Both. Usually it's a very small weight, a very small volume, but that should be accounted for in the mix design. So yes, the weight of the pigment and the volume of the pigment should be accounted for. Probably not going to be a huge deal if you don't account for the volume, but it is a known volume, and so it should be accounted for.
All right, that's the only one that came in.
All right, well, let's go ahead and talk about alternate testing for concrete compressive strength. This chapter, the title of the chapter is not really accurate because some of these alternate methods that we're going to be talking about aren't necessarily used for strength. Most of them are, but some of them are not. Probably a better title for the chapter is alternate testing for concrete properties as opposed to just compressive strength. But we're going to be looking at some alternative methods for assessing the overall quality of our concrete, strength being one of the primary ways that we assess quality. And so as we go through this, we're going to be talking about correlation testing and how we go about doing a correlation test based on data that we've generated. And so certainly, if you have any questions as we go along, then I'll stop and see if you have any questions. But I think everybody's probably most interested in getting on to Chapter 7. So we'll certainly give Chapter 6 a thorough review, but we'll make sure that we have plenty of time to spend on Chapter 7 in case there are questions for Chapter 7. That way we've got plenty of time to do the example problems in Chapter 7 and that sort of thing. So without any further delay, let's go ahead and talk about concrete quality evaluation and some alternate methods. So the primary way that we evaluate the strength of concrete is through concrete test cylinders. You've seen terminology in the book talking about how the 6x12 cylinder is the standard. So just want to clarify that when we use that term standard, what we mean by that. That term means the method that all other methods must be referenced to. So it doesn't mean it's not standard in the sense that it's typical, that it's what most people use. It's standard in the sense that no matter what you're using to evaluate concrete strength, either you have to compare that to the strength of a 6x12 cylinder, or somebody else has already done that and shown that whatever method you're using within a reasonable degree of error will provide a result that is similar to what a 6x12 cylinder would indicate. So that's what we mean by standard. We mean standard in this sense is what everything else gets referenced to. So an analogy would be if you're a car person, maybe you're an American sports car person, you're really into American sports cars. And so in your mind, the standard for American sports cars may be the Corvette. That doesn't mean that everybody drives a Corvette, but what it means is that in your mind, all other American sports cars ultimately gets compared to a Corvette, and how it stacks up compared to a Corvette is how good. That's how you evaluate how good the car is. And so that's what we mean here by 6x12 cylinder is the standard, in that these other methods, how well they compare to a 6x12 cylinder, that really determines how good these methods are. So ASTM C31 covers making and curing cylinders, and ASTM C39 covers the testing for compressive strength of cylinders. In your book, it mentions that the load rate for testing should be 20 to 50 psi per second. ASTM C39 has been revised in recent years to tighten up the tolerance on that load rate. So you may want to make a note in your book that the current requirement is 35 psi plus or minus 7 psi per second. So it's 28 to 42 psi per second is the acceptable loading rate. So make sure that you've got that noted in your book so that you remember that when you're studying, that the current requirement is 28 to 42 psi per second. So what that load rate means, it's kind of hard to visualize 28 to 42 psi per second. What does that mean when I'm standing there in front of a test machine doing a test? Well, it means a lot if you've got a digital readout that's showing you the load rate, so you know that as long as you're between 28 and 42, you're good. But oftentimes, plants have analog compression test machines, or maybe they have digital compression test machines that they're only showing the load that's applied. It's not showing the actual load rate. So if you're working with a machine that only indicates load, then a good rule of thumb is for a 6x12 cylinder, if you're in this target load rate range, then you should be loading the 6x12 cylinder at around 1,000 pounds per second. So you can watch the dial indicator or the digital readout, you can watch the clock, and so long as the load's being applied somewhere in the neighborhood of 1,000 pounds per second, then you're good on a 6x12 cylinder. Now for a 4x8 cylinder, a good rule of thumb is around 500 pounds per second. So again, you can watch the load being applied from the dial or the digital readout. Keep an eye on the clock, and so long as your load rate is around 500 pounds per second, then you are in the target load rate range for ASTM C39, and you're okay for a 4x8 cylinder. All right, cylinders smaller than 6x12 can be used, but there are some things that we need to keep in mind. One is that the mix design has to be suitable for using a smaller cylinder. And the way we can evaluate that is by looking at the maximum aggregate size in our mix design. The maximum aggregate size has to be less than or equal to 1/3 the test cylinder diameter. So to use a 4x8 cylinder, that means that our mix design can have a maximum aggregate size of 1 1/3 inches. Most precast plants, we're going to be using 3/4 inch aggregate or smaller. So usually the maximum aggregate size is not an issue when using 4x8 cylinders at a precast plant. If you're going to use a cylinder smaller than 6x12, correlation testing is required. Correlation testing is where you do tests for the smaller cylinder and compare those results to the results from 6x12 cylinders, statistically evaluate those results and determine whether or not the smaller cylinder accurately, within a reasonable error, replicates the strength that would be indicated by a 6x12 cylinder. Now, thankfully for 4x8 cylinders, a lot of correlation testing has been done over the years, and so PCI no longer requires that a plant do correlation testing if they want to make the transition from 6x12 to 4x8 cylinders. They can just start using 4x8 cylinders as far as PCI is concerned. Now, if you're going to be using a different size cylinder, say a 3x6, then you would need to do correlation testing, comparing the strength indicated from those 3x6 cylinders to the strength indicated by a 6x12 cylinder made from the same mix design at the same time, and statistically show that the results of the smaller cylinder are reasonably close to the results of the 6x12 cylinder. All right, so there are some advantages to using smaller cylinders. Those are shown in a table on page 6.2. The 4x8 cylinder has a volume that's less than 1/3 the volume of a 6x12 cylinder, so you need less concrete, a smaller sample to make your 4x8 cylinders. Likewise, the weight of 4x8 cylinders is less than 1/3 the weight of 6x12 cylinders, so they're easier to move around, easier to transport by hand. Using smaller cylinders also saves wear and tear on your compression machine. So as shown there in the table, if you have a 6,000 psi required strength, for a 4x8 cylinder, you would only have to apply a load of a little over 75,000 pounds, whereas for a 6x12 cylinder, you would have to go up to almost 170,000 pounds. So we're looking at loads that are significantly lower when using 4x8 cylinders. So that does help to save maintenance costs on our compression test machine. Also, they take up less room in the storage area, whether we're using a 100% humidity room or we have a tank that we're storing our cylinders in. We can get a lot more 4x8 cylinders in the same space than we can 6x12 cylinders. So storage space is also an advantage to using 4x8 cylinders. All right, so just like the 6x12 cylinder is our standard cylinder size, cast end caps or sulfur end caps are the standard capping method. Again, that doesn't mean that everybody uses sulfur end caps. It just means that that is what all other methods have to get compared to. So what most plants use today is unbonded caps, neoprene caps. That's covered by ASTM C1231. At the bottom of page 6.2, it notes that ASTM C1231 covers concrete strengths between 1,500 and 7,000 psi. You can go ahead and note that ASTM C1231 now covers concrete strengths up to 12,000 psi. So you can go beyond 7,000 psi with a neoprene cap. You can go up to 12,000 psi now based on ASTM 1231. All right, so neoprene caps do require correlation to bonded end caps. Again, a lot of correlation testing has been done such that PCI does not require that plants who are switching from bonded end caps to unbonded caps have to do correlation testing. They can go ahead and make that change based on the correlation testing that has been done in the past. So if you're not familiar with neoprene caps, a schematic of what a cap set looks like is shown in figure 6.1 on page 6.3. So we have a steel end cap in which a neoprene cap fits. And so we have one of those combination steel and neoprene caps on each end of the cylinder. The hardness of the neoprene is dictated by the concrete strength. So we should use a Shore A 50 durometer pad for lower strength concretes. Generally, for concretes less than 7,000 psi, we should use a 50 durometer pad. Definitely, if the concrete is less than 4,000 psi, we should use a 50 durometer pad. The hardness of the 70 durometer and a low strength of below 4,000 psi can cause a premature failure of the concrete. So definitely below 4,000, we need to use a 50 durometer, but the 50 durometer can be used up to around 70 or up to around 7,000 psi. All right, so at those higher strengths above 4,000 and certainly above 7,000, the 70 durometer pad should be used. We need to monitor how many times the neoprene pads are used. For the lower durometer pad and concrete strengths below 7,000 psi, we can generally use the pads 100 times. We should, what most plants do is they'll, after 50 uses, they'll flip the pads so that they get used 50 times on each side. For the higher durometer pad at strengths above 7,000 psi, the pads should only be used 50 times, so flipped after 25 uses. What some plants do is they have two different sets of end caps. One set is for stripping strengths, and they have 50 durometer pads. And then the other set of end caps is for 28-day strength, and they have 70 durometer pads. And so based on the anticipated strength of the concrete, they will choose which set of caps is most appropriate. All right, there is a mention of a protective enclosure should be used around the compression test machine when unbonded caps are being used. Even when bonded caps are used, we should have a protective enclosure just in case there are splinters from the concrete, especially at higher strengths. The concrete tends to explode. and so we need a protective enclosure. An added safety consideration when using an unbonded end cap is that if we don't get the cylinder centered in the test machine, then at high loads and eccentric loading, the cylinder and the end caps could be ejected from the machine. And so the protective enclosure would help to protect anyone in the lab from flying steel end caps, which that's definitely not something you would want to encounter at a high rate of speed. So just keep that in mind. All right, the first alternative method that we're going to talk about is the pulse velocity method, ASTM C597. This is one of those methods that really doesn't do a good job of telling us the concrete strength. Really, this method is more useful in determining the relative quality of the concrete. So that's one of the drawbacks of this method, is it does not give us precise indications of strength. One of the advantages to this method is that it can be used on in-place concrete. It doesn't damage the concrete further, and so it can be used on in-place structures to establish the relative quality of the concrete. The way this test works is we have a transmitter and a receiver. We place the transmitter on one side of the concrete that is being tested, the receiver on the other side. The transmitter transmits a sound wave through the concrete. Based on the speed with which the sound is transmitted, we can make some assessments of the quality of the concrete. Generally, higher quality concrete is going to transmit the sound wave at a higher speed. And so if we get transmission speed of above 12,000 feet per second, then that's indicative of good quality concrete. If the transmission speed is less than 10,000 feet per second, that's usually indicative of cracks or voids or a poor quality of concrete. If you're somewhere in between 10 and 12,000 feet per second, then you can't really say that it's good quality concrete, but on the other hand, it doesn't really meet the criteria for being poor quality either. You know that there's an issue of some sort, but you're not really sure what it is. So again, this method is not for precise evaluation of concrete strength, but rather it gives you a relative sense of the quality of the concrete. Next is the rebound number, ASTM C805. This has different names. You may have heard the rebound hammer, Schmidt hammer. So these are all referring to the same method of evaluating concrete strength. That's covered by ASTM C805. This is probably the most common alternative method that we see used in precast plants, and we really don't see it all that often. But usually if a plant is going to make some assessment of concrete strength outside of using a cylinder, then the rebound hammer or the Schmidt hammer, that's another name, is what they're going to use. So for those of you that haven't seen this device before, basically it is a metal cylinder that can be held in the hand. It's a couple of inches in diameter. Inside of that metal cylinder is a spring-loaded mechanism that controls the release of a solid steel pin. And the way this test method gives you an indication of strength is through a gauge on the side of the cylinder, of the steel cylinder, of the rebound hammer. As that steel pin is released and it hits the concrete and bounces off, the amount of energy that's reflected back into the pin is indicated on the gauge. And so the more energy that's reflected back into the pin, that's indicative of a harder concrete. And so we get the indication of a higher concrete strength. So with a low concrete strength, that energy is going to predominantly be absorbed by the concrete, not reflected back. And so we're going to get a low rebound number. So in order to use a rebound hammer to get anywhere close to an accurate assessment of concrete strength, we need to correlate the rebound hammer to the actual mix design with which it is being used. Rebound hammers come from the manufacturer with correlation curves that show the estimated concrete strength based on a given rebound number. However, those curves are based on a generic mix design, and how the hammer interacts with your particular mix design may be different. And so for that reason, if you are going to use a rebound hammer on a regular basis at a plant, then you need to do correlation testing so that you develop data and a correlation curve that is specific to the mix design or mixed designs that you're going to have in use at your plant. So the hammer can be used either in the vertical position or the horizontal position, but it's going to give different readings based on the position in which it's used. And so we need to have a correlation curve for both the vertical position and the horizontal position if it's going to be used potentially in practice in both positions. So the way we go about developing our correlation data using a rebound hammer is we would make some 6x12 cylinders. They do have to be 6x12 cylinders. A 4x8 cylinder would not work for a rebound hammer correlation because the 4x8 cylinder doesn't have enough mass to give reliable results. So we do need to use 6x12 cylinders. We would make a number of 6x12 cylinders, and then over a period of time we would test cylinders at different anticipated concrete strengths. But before we test the cylinder to failure, we're going to use the rebound hammer on the cylinder. So to develop data for our hammer in the vertical position, we can set the cylinder on a good solid surface, such as the slab in our lab. We don't want to put it on a soft surface, such as soil, or on an elevated surface, such as a table, because some of the energy from the rebound hammer can be dissipated through the support. So we need to be on a good, solid, rigid surface, such as a concrete slab. And we're going to take several readings on the end of that cylinder, then flip it over and take several other rebound readings. And then we're going to average all of those readings together to get an average rebound number. Then put the cylinder in the test machine, test it to failure, and that gives you a concrete strength. So now we have a data point. We've got a concrete strength, and we have a correlated rebound number associated with that strength. So if we do this over a period of time for a range of concrete strengths, then we can use that data to develop a correlation curve. And so we'll talk in detail about how we go about developing a correlation curve in just a few minutes as we get a little bit further along into the chapter. All right, but the key thing to keep in mind here is that we have to go through this process for every mix design that the rebound hammer is going to be used. All right, so I just described how to get your correlation data if the hammer is going to be used in the vertical position. We have to go through a slightly different process if we're going to use the hammer in the horizontal position. So using the hammer in the horizontal position, we're going to put the cylinder in the machine, and we're going to put just enough load on the cylinder so that it is rigidly held in place. So we're not going to break the cylinder yet, but we're going to put a few thousand pounds on it just so it is definitely not going to move. And then we're going to, using the hammer in the horizontal position, take several readings from the side of the cylinder. We can then take the load off the cylinder, rotate it, and hit the cylinder again, rotate it, hit the cylinder again. So by doing this, we get several rebound readings in the horizontal position off the cylinder. We can average those to get a rebound number. We then test the cylinder to failure, and so that gives us a strength. And so now we have a data point for our correlation curve. That is a concrete strength and a representative rebound number. All right, another test method that can be used is penetration resistance, ASTM C803. This is probably the second most common test I see used in precast plants, but it is used much less frequently than the rebound hammer. I've only seen this used a handful of times at precast plants. The way this test works is that we're going to shoot a steel pin into the concrete, and based on how deeply the pin penetrates the concrete, we're going to estimate the concrete strength. So the more deeply the pin penetrates the concrete, the lower the concrete strength. Generally, we're going to shoot 3 pins into the concrete and average the penetration for those 3 as we establish our concrete strength. Keep in mind that there are some things that can interfere with this test. If our mix design incorporates larger coarse aggregate particles, then if one of the pins happens to hit right on a coarse aggregate particle, then that's going to affect the average of our 3 readings. We do have to do correlation testing for penetration resistance. So we should do a correlation curve if we're going to be using the penetration resistance method as the determining factor for when we can strip concrete. So the way we would develop correlation data for penetration resistance is to cast a block of concrete. At the same time, cast several cylinders from the same mix. Then over a period of time, we can shoot pins into the concrete block and determine an average penetration resistance and test a cylinder. So the cylinder gives us a strength, and the shooting the pins into the block gives us a penetration value, and so that gives us a data point. So if we do this multiple times over a period of time, over a range of concrete strengths, then that will help us to develop a correlation curve for the penetration resistance test. This is also referred to as a Windsor probe test, so maybe you've heard of the Windsor probe test. Next is pull-out strength, ASTM C900. This is actually a pretty accurate way of assessing concrete compressive strength. The way this test works is that we cast a steel disc into the surface of our precast concrete. That disc has a threaded collar in the center that's exposed to the surface of the concrete. When we want to test the strength, we have a device that threads into that collar on the plate that's in the concrete. That device has a load gauge on it, and so we start cranking that gauge and shearing the steel plate out of the surface of the concrete. And based on the amount of force that's needed to pull the plate out of the concrete, we can then estimate the compressive strength. So this is a pretty accurate way of assessing concrete strength, but it does have some drawbacks. One is that you have to know you're going to need to use it when the product is cast. Oftentimes in precast plants, we're using cylinders to evaluate strength, but the reason we might want to use an alternative method is because something happened to our cylinders. Either they got damaged, or maybe we've used all of our cylinders and we still haven't made the required strength, and so we need some alternative method. So with pull-out strength, you have to know beforehand that you're going to need to use the method. And so typically that's not really going to be applicable to precast operations. Another drawback to this method is that it does damage the surface of the precast unit, and so that's going to require that the test be done in an inconspicuous location, that there's going to be some patching that needs to be done. So where we see this test used most commonly is in cast-in-place operations, such as for framed slabs in multi-story construction. They'll use the pull-out strength method to determine when the slab has achieved the required strength that they can start removing shoring. So again, it is a pretty accurate way of assessing concrete strength. It just doesn't lend itself well to precast operations. Next is cores and sawn beams, which are covered by ASTM C42. Chance talked a little bit about ASTM C42 yesterday. There is one thing in your book that I want to draw your attention to, just as a good rule of thumb. On page 6.7, the first paragraph under cores and sawed beams, so that paragraph right in the middle of the page, the last sentence in that paragraph says, when in doubt, have the design engineer select the location for the cores or prisms. So cores and sawn beams are going to be cut directly from the precast unit. And so the book says, when in doubt, have the design engineer select the location for where those cores or sawn beams are going to be cut. I recommend that you mark through the first 3 words of that sentence so that the sentence says, have the design engineer select the location for the cores or prisms. All right, that should be the responsibility of the design engineer to determine the best location for cutting the product. That responsibility should not fall to Bobby, our shipping foreman, or our yard foreman. He shouldn't have to carry the responsibility of determining where best to cut a bridge girder to cut cores. That should be the responsibility of the design engineer. All right, as Chance may have mentioned, the strength indicated by cores may not relate directly to the actual strength of the concrete. For that reason, ASTM C42 requires that the average of 3 cores achieve only 85% of the target strength. So one of the reasons why the cores are not required to reach 100% of the target strength is that the perimeter of the core doesn't confine the coarse aggregate. So if you look at a cylinder, all of the aggregate particles are confined within the matrix of the concrete around the perimeter. But if you look at a core, the coarse aggregate in the perimeter of the core has been cut, and it is not fully confined within the matrix of the concrete. And so what that means is that we don't get the full cross-sectional area of the core effective in resisting the load that's being applied during testing. And so in recognition of that, ASTM C42 says that cores only need to achieve 85% of the required strength. Now keep in mind, that's an ASTM C42 requirement. If a plant is doing work for a DOT or some other government agency, that government agency may have their own specification with regard to cores. And their specification may require that the core achieve 100% of the required strength. All right, that is their prerogative to do that as the owner of the project. So just be aware, if it is a DOT project or other government agency, that they may have their own specification and they may require that cores achieve 100% of the required strength. If it's a commercial project, generally ASTM C42 is going to be referenced, and so the cores should achieve 85% of the required strength. Also, as it mentions there in the book, no one core should be below 75% of the required strength. Ideally, the length or the height of the core is going to be twice the diameter. Just like for our cylinders, the aspect ratio is generally 2. The height is twice the diameter. And so we want to keep the same aspect ratio for our cores. However, we can have an aspect ratio less than 2, but definitely not less than 1. So at a bare minimum, the length of the core should be equal to or greater than the diameter of the core. The moisture condition of the core will affect the indicated strength. Previous versions of ASTM C42 did not really get into specifying how the cores should be stored prior to testing. But more recent versions of ASTM C42 do dictate storage requirements in recognition that the moisture content of the core does affect the strength. I think currently ASTM C42 requires that within a certain period of time of being cut, the cores are supposed to be placed in a sealed container, such as a Ziploc bag, and that they should be stored in that condition until within a certain amount of time of being tested. So this way, there's a more consistent level of moisture, there's more repeatability in the test results. But one way to get more strength out of a core is to dry it out, and generally it's going to test higher than a wet core would test. All right, so let's talk a little bit about correlation curves. So there's table 6.2 in your book. On page 6.5, we're going to use that data, those 14 data points, to develop a correlation curve. And there's a couple of different ways that we can develop a correlation curve. One way is to use our computer. We can set up a spreadsheet to do all of the analysis for us. Matter of fact, if you flip over to the back of your book to Appendix D, Appendix D gives you all of the equations that you would need to set up a spreadsheet to do a correlation analysis for you. There is one typo in Appendix D. It's on page D.2. And right in the middle of page D.2, there's an equation for alpha. And it says that alpha is equal to 100 minus the confidence percentage over 100. And so there is a slight typo there. It should be 100 minus the confidence percentage. All of that is divided by 100. So it's not 100, and then you subtract from that the confidence percentage over 100. You subtract the confidence percentage from 100, and then you divide by 100. All right, so other than that, all of those equations there should be good. Would be very helpful if you want to set up a spreadsheet to do some correlation analysis. So if you do it by computer, then page 611 shows you some of the output by doing it this way. Shows you the tabular values, shows a graph with your data plotted, and then the confidence limit bands are shown. So that's one way of developing a correlation curve. Another way of developing a correlation curve, which if you don't want to go through the hassle of setting up a spreadsheet, is just to do it by hand. And depending on how much data you've got, by hand may be quicker and easier than doing it by computer. So a hand-drawn correlation curve is shown on page 6.9 in figure 6.3. So here's the data we're going to be using from table 6.2, and then here is figure 6.3, the hand-drawn curve, and then here's figure 6.4, the computer-generated curve. So we're going to primarily focus on the hand-drawn curve. Now you'll notice that on the hand-drawn curve that their lines are not labeled correctly. So looking at the computer-generated curve, it's correct. They're showing the confidence bands, and they have those labeled as 95% confidence bands. But if you look at the hand-drawn curve, they've got those bands labeled as 80%. So that is a typo. 80% bands would be closer in to the 50% line. And so on the overhead here, we've sketched in the 80% bands to show where they would be. And then the bands that are in your book, the bands that are further out, those are actually the 95% confidence limit bands. All right, so the way this curve works, the way you would go about drawing this curve by hand, is you would plot all of your data points. So in this case, we've got 14 data points. Each data point is represented by a rebound number and a compressive strength. So we plot those data points on our graph. And then if we draw a line right through the middle of those data points, that is our average. So using that line right through the middle, that would give us the average strength based on a given rebound number. So if we've got a rebound number of 35, then using that dashed line right through the middle of our data, if we go up to that 50% line and then go over and read our compressive strength, we get something like 3,800 psi. And so what that's telling us is that on average for a rebound number of 35, we've got a compressive strength of 3,800 psi. All right, but what that also means is that 50% of the time, the strength is actually going to be greater than 3,800 psi, but 50% of the time it's going to be less than 3,800 psi. So when it comes to stripping strength for a pre-stressed concrete bed, we don't want to have a 50% confidence. We want to have a 95% confidence that the concrete has achieved the required strength. And so that's why we need 95% confidence limit lines. So if we're going to draw these 95% confidence limit lines by hand, the way that we would do that is we would start with our 50% confidence limit line, and then we would draw our 95% lines, and they're going to be somewhat parallel to that 50% line. But the question is, how far away from that 50% line do we go in drawing our 95% confidence limit lines? Well, if we had 100 data points, then our 50% line should be drawn such that half of the points are on one side of the line and half of the points are on the other side of the line. So using that same logic, if we want to draw a 95% confidence limit line, then that means if we've got 100 data points, 95 of them should be on one side of the line and only 5 of them should be on the other side of the line. All right, so if you've got a lot of data, then drawing your 95% confidence limit lines is actually pretty easy because all you have to do is just make sure that 95% of your data is on one side of the line and 5% of data is on the other side of the line. Okay, in our case, we only have 14 data points. So 95% of 14 is 13 point something. So essentially all of our data points are going to be on one side of the line. But the line should be fairly close to a data point. And so that's how we went about drawing in our 95% confidence limit lines. And if you look at the computer generated line, you can see the same thing. So none of our data points are outside the line. All 14 are on one side of the 95% confidence limit bands because we have so few data points that 95% of our data is essentially all of the data. 5% is less than 1. So that's how we go about deriving our 95% confidence limit bands. It makes it much easier to do it by hand if we have a lot of data, because it's much easier to visualize 95% of that data being on one side of the line and only 5% being on the other side of the line. All right, so notice that we've got two 95% confidence limit lines. We've got a lower line and we've got an upper line. Both of those are 95% confidence limit lines. It's just that they're 95% confident of two different things. So going back to our rebound number of 35, if we go up to that lower 95% confidence limit line, we get a compressive strength reading of 3,000 psi, maybe just a little bit over 3,000 psi. So what that's telling us is that we're 95% confident that at a rebound number of 35, that concrete is at least 3,000 psi in strength. 95% confident. There's only a 5% chance that it's less than 3,000 psi. All right, so that's the kind of confidence we want to have in our values. All right, conversely, if we go up to that top 95% confidence limit line using a rebound number of 35, we go over and we read a concrete strength of 4,700 psi. All right, 4,700 psi. So what that's telling us is that we are 95% sure that the concrete strength is less than 4,700 psi. There's only a 5% chance that it's above 4,700 psi. So that upper bound 95% confidence limit line, really, we're not going to use that. It's the lower one that we're going to use. So what I would recommend is that if you're developing a correlation curve for a plant, just plot the lower bound 95% confidence limit line and leave the upper bound 95% confidence limit line off so that you don't have to worry about somebody inappropriately using the wrong 95% confidence limit line. So just plot the lower bound line, leave the upper bound line off, and that will make it easier to read. All right, so that is how we go about developing correlation curves. You can either do it hand-drawn or you can do it using a computer. Either way is acceptable. The hand-drawn curve may actually be quicker if you only have a few data points. The hand-drawn curve will be more accurate if you have a lot of data points, but it will take more time to plot in all of those points. So you can decide which is the better fit for you. All right, and that is it for chapter 6. Do we have any questions?
We did have a couple of questions.
Okay.
The first one is, according to ASTM C33, there's a difference between nominal and maximum aggregate size. Does the testing go that far in depth, or is it general specification?
It's general. Matter of fact, the TM103 probably uses the nominal and the maximum as synonymous. So yeah, the test is not going to get that deeply into the weeds.
And then the next one we have is, can any commercial project, i.e. non-DOT or non-governmental, specify core strength of more than 85% required strength?
Yes. The specifier for any project can do whatever they want to do. It's just more than likely for a commercial project, they're going to rely on ASTM requirements. It's less likely that they would go off the reservation and start specifying things that are not standard ASTM. So definitely it can happen. So you should look at the specification, but more than likely if it's a commercial project, they're going to reference ASTM C42. I know for our design projects here at Ross Bryan Associates, we always reference the ASTM standards unless it's a project that we're doing for a government agency and we have to reference their specifications. But if it's not a government agency, we're referencing ASTM specifications and very rarely deviating from those.
All right, those were the only two that came in.
All right, well, let's take a little break before we dive into chapter 7. I've got that it is 2:41, 2:42 Central Time. So let's just take an 18-minute break and start back at the top of the hour. And so that will give us a couple of hours for chapter 7. That should be plenty of time to go through the information relatively slowly, look at each example problem, step through it, and then give you guys time to ask questions if you have any. So let's start back at the top of the hour.
All right, sounds great.
All right, well, welcome back. Let's go ahead and get going with Chapter 7, Pre-stressing deflected strands. And this chapter will finish out today's session. So we've got a couple of hours to spend on Chapter 7. Probably will not take that amount of time unless you guys have a lot of questions, which if you do, that's good. So let's go ahead and dive into it. So in Chapter 7, we're going to be talking about pre-stressing deflected strands. Now there's some terms that we'll be using interchangeably, and you will hear them used at plants interchangeably. Draped, harped, and deflected all refer to the same condition. So there isn't any technical difference between those three words. So draped, harped, and deflected all basically mean the same thing. So I may use all three of those terms as we go through our discussion today, and you're likely to hear all three of those terms used out in the industry as well. So certainly deflecting pre-stressing strands is a bit more complicated than tensioning the straight strands. And so that raises the question, if it is more complicated, then why bother doing it? What's the big advantage to using deflected pre-stressing strands? And really there's two advantages. One is we do get enhanced capacity from the strands when they are in the deflected position than when they are in the straight position, especially for strands that are higher up in the cross section. If we can push those strands down into the lower portion of the cross section, especially at critical locations like at mid-span, then that gives us significantly more capacity, load carrying capacity from the beam than we would have if those strands were just straight. So here is an example of how we get this enhanced capacity. So the upper part of this diagram, we're looking at the side view of a beam. So it would be supported on either end. And the dashed lines represent the straight strands. And then the solid lines represent those two upper strands being deflected or harped. So that's what that upper figure is showing us. Now the lower diagram is something that if you have an engineering background, you may be familiar with. But if you don't have an engineering background, which most of the people we have on this class probably don't, then this probably doesn't mean a whole lot to you, this diagram. But this is what we refer to as a moment diagram. And the moment in a beam, which it's kind of an odd term, the moment in a beam, but the moment in the beam is depicting how the energy in the beam is distributed as that beam is resisting an applied load. And so generally, if we have a beam that just has a uniform load across the length, think about a bridge girder with cars on the bridge, bumper to bumper, rush hour traffic, so you've just got a uniform load along the full length of the span. Then the moment in that bridge girder, the moment in that beam as it resists that load, is going to vary from a peak at the center of the span to zero at the ends of the span. And so the arching portion of this diagram represents the moment in the beam due to those cars bumper to bumper. So at the ends of the beam, the moment is zero, and it goes up to the top of the arch right in the middle of the span. So that's essentially the moment demand on that beam. Now with straight strand pre-stressing, once the strands are developed, we have a constant moment capacity in the beam. And so that's represented by that lower straight line that just is horizontal along the length of the beam. That represents the capacity of the beam, the moment capacity with straight strands. All right, the straight lines that form kind of a tent shape that go up to a peak at the center, those lines represent the moment capacity of the beam when the strands are draped. So the further down in the cross section of the beam the strands are located, the more moment capacity we get out of those strands. So that's why the moment capacity is flat for the straight strands, because they're at the same elevation in the beam throughout the length of the beam. But the moment capacity goes up for the deflected strands, because as the deflected strands get lower in the cross section, they provide more capacity. So in this generic example, with straight strands, this beam does not have enough capacity to carry the load. The arch is greater than that flat horizontal line, which represents the capacity, so this beam does not have adequate capacity. However, if we deflect the strands, then our moment capacity becomes that tent shape that peaks right at the center, has the point right at the center. And you can see with that moment capacity, the capacity is always greater than or equal to the actual moment demand represented by the arching or the curved line. So straight strands, we don't have adequate capacity. Draped strands, we do have adequate capacity in this example. All right, another thing to keep in mind as we talk about draped strand pre-stressing is that there are a couple of different ways that we can go about draping the pre-stressing strands in a bed. One way that we can do that is we can stream the strands in the bed in the draped position and tension them in that draped position. Okay, so that's one option that's available to us. Another option would be to string the strands in the bed in the straight position, and then after they're tensioned, to go back and either push them down or pull them up into the draped position. Okay, either of these methods is acceptable, and it really depends on how the bed was designed as to how the plant is going to go about deflecting the pre-stressing strands. For some beds, they were designed to be tensioned in the draped position. Other beds were designed to where they could be tensioned straight and then pushed down or pulled up into the draped position. The advantage to tensioning in the draped position is that the tensioning operation is simplified. We conduct the tensioning operation the same way we would with a straight strand. We just put in initial force on the strand, mark the strand, put the final force on the strand, measure our net elongation, compare that to our calculated elongation, and then so long as we're in tolerance, we're done. So the tensioning operation is done the same way it would be if they were straight strands. However, the disadvantage to tensioning in the deflected shape is that we get friction that builds up at each location where the strand is held up or it's held down. And so for a long bed, the accumulating friction along the length of the bed may make it difficult for us to tension the strands in the deflected position and get them in within tolerance requirements. Okay, so that's the downside to tensioning in the deflected position. All right, tensioning in the straight position and then deflecting the strands afterward, we kind of have opposite pluses and minuses. The plus of doing this is that we eliminate the friction at the hold up and hold down points that interferes with our tensioning tolerance. And so it's usually easy to get the strands tensioned within required tolerances if we tension them straight and then deflect them afterwards. The downside to this process is it does complicate our tensioning operation in that after we apply the force to the strand using our jack, we have to go back and then do a secondary procedure where we push the strands down into the draped position or pull them up into the draped position. All right, so it takes more time to do the tensioning, and there are some safety concerns that we have as well that we have to make sure that are addressed in that secondary procedure. All right, so those are the two primary ways that we go about tensioning strands that are going to be in the deflected position. And actually, we can use both of these methods in combination with each other. A plant may have a really long bridge girder bed that the bed is set up to where they can push the strands down into the draped position after they've been tensioned. But because it takes a long time to do that, what they may do is set up, if they can get 3 beams in the bed, they may set up 2 of those beams in the deflected shape, tension the strands in the deflected position, and then afterwards go back and push the strands down into the draped position for that 3rd beam. So they're actually using a combination of these 2 tensioning methods, and that's acceptable as well. All right, let's look at figure 7.1a. In this diagram, we have a 3-beam setup. Each beam is length L. And we have hold up and hold down points along the length of the strand represented by the letters A through J. So A, D, G, and J are what are referred to as hold up points because it's pretty self-explanatory. Those are the locations where the strand is being held in the upper position. And then at B, C, E, F, H, and I, we have hold down points. So these are the locations where the strand is being held in the lower position. All right, so in figure 7.1a, we've got 3 beams. Each beam has a 2-point hold down. Usually these 2-point hold downs are going to be on either side of the center line of the span of the beam. They're going to be equal distant from the center line of the span of the beam. Okay, compare that to figure 7.1b. Again, we have 3 beams set up. Locations A, C, D, F, G, and I represent hold up locations, and locations B, E, and H represent hold down locations. So in this case, we have a single point hold down that's located at the approximate center of the span of each of the 3 beams. So figure 7.1a, we have 2-point hold downs in each beam. In figure 7.1b, we have a single point hold down in each beam. For bridge girders, we typically see a 2-point hold down, such as figure 7.1a. And for double T's, we typically see a single point hold down, such as figure 7.1b. In figure 7.2a, we are tensioning after the strand is in its final deflected position. So in this condition, we're going to string the strand along the length of the bed, string it over the hold up locations and under the hold down locations, and then we're going to tension the strand in that draped position. So notice that each of our hold up and hold down locations, we have a little circle there that's labeled as a roller. So our hold up and hold down devices have rollers incorporated. That helps to minimize the friction that builds up at each of those deflection points. So if we didn't have rollers or some other means of dissipating friction at those points, we would get a significant amount of friction such that we would be unable to tension the strand in the draped position and get the strand tensioned within tolerance requirements. But by using rollers, typically we can tension the strand within tolerance requirements, just depending on how long the bed is and how many hold up and hold down locations there are along the length of the bed. Okay, contrast that with figure 7.2b. In figure 7.2b, we are tensioning the strand in the straight position, and then afterwards we're coming back and we're picking the strand up into the draped position. So again, we have 2 beams in the bed. Each beam has a 2-point hold down, but instead of tensioning the strands in the draped position, we're tensioning the strands straight, and then we're coming back and picking the strand up at the hold up location such that it ends up being in our deflected shape. Notice that each of the hold up locations are numbered, and we don't number from one end to the other, but instead we start in the middle. So this is the number sequence that we're going to use in installing the hold up points. So typically if we tension the strands in the straight position and then pick them up or push them down into the draped position, we're going to start in the center of the bed, and then we're going to alternate from side to side until all of our hold up or hold down points have been properly installed. By starting at the center of the bed and alternating from side to side, this helps to minimize the variation in force distribution along the length of the strand. If we started at one end of the bed and worked our way to the other end of the bed, installing these hold-up points, we have a greater risk of a differential in force in the strand between one end of the bed and the other end. In figure 7.2c, again, we're tensioning the strand in the straight position, but afterwards we're pushing it down into the draped position. So again, the dashed lines represent the draped position, and the solid line represents the tensioned position. So again, the hold down locations are numbered. So we're going to start there on the left at number 1, then go over to the other side, number 2, number 3, and then back to number 4. So again, we're trying to do the hold down locations in a symmetrical pattern so that we minimize the force variation in the strand from one end of the bed to the other. Now, while we're looking at this figure, notice that the length of the strand in the draped position is longer than the length of the strand in the straight position. So what that means is that when we tension the strand in the straight position and then we push the strand down into the draped position, we're actually adding elongation to the strand. If we're adding elongation to the strand, then we're increasing the force in the strand. So before we can tension the strand in the straight position, we have to calculate how much force that strand is going to gain when it goes from the straight position to the draped position. And then we're going to deduct that force from our tensioning force, so that once the strand is tensioned with the jack in the straight position, and then it's pushed down into the draped position, and it's gained some force, it's at the required force specified by the design engineer. So if I calculate that pushing the strand down into the drape position is going to add 6,000 pounds to the force in the strand, and I have a target tension force of 30,000 pounds as dictated by the engineer, then I'm going to tension the strand in the straight position to only 24,000 pounds because I know it's going to gain another 6,000 pounds when I push it down into the draped position, so that it ends up, once everything is said and done, at 30,000 pounds, which is the required force dictated by the engineer. Okay, so some things to keep in mind when we tension strands in the deflected position. We want to reduce the friction at the hold up and hold down locations by using rollers. There's other ways that we can reduce the friction at those points as well that we'll talk about as we go along. Typically, our hold down devices and hold up devices are going to be capable of rotating so that they can geometrically align with the force vector that is in the strand. So a good representation of this is figure 7.3. I'm sorry, yeah, figure 7.3, not page 7.3, but figure 7.3. You can see that this hold down device can start out vertical, but then it can rotate as the strands are tensioned so that it properly aligns with the geometry of the strand in the draped position. So this helps to distribute the force to our hold down devices correctly so that there's no eccentricity in the device. And it also helps with mitigating any potential friction that would build up at that hold down location as well. All right, our tolerances for tensioning are the same as you learned in level 2. For straight strands, we'll cover those. We'll look at those in a little bit more detail in just a minute. But we don't have to learn any new tolerances for level 3. It's the same tensioning tolerances that you learned in level 2. Figure 7.4 and figure 7.5 represent a couple of different ways that we can hold up the strands at the hold up locations. Figure 7.4 is a hold up tower. This is like a column that sits on the soffit of the beam bed. This tower is typically, or column is typically made out of steel plates. So it acts as a column and it can resist that compressive load, that downward force that is applied when the strands are in the draped position. Notice that there are holes, a variety of holes in the tower so that we can adjust the location of the strand to the required elevation so that we have the appropriate drape in the strand after tensioning. So typically we would stick a pin with a roller through the desired elevation hole before we string the strand, and that's going to match up with the required geometry of the strand in the bed. In figure 7.5, we have another way of holding up the strands at the hold-up point. This is a portal frame that spans over the bed. Notice at the top of that portal frame is something that looks like a hydraulic ram, and that's because it is a hydraulic ram. So this bed is set up to where the strands can be tensioned in the straight position down low and then jacked up with the hydraulic ram into the draped position that's shown in the figure. All right, so this bed is set up for tensioning in the straight position down low and then lifting the strands into the draped position after they've been tensioned in the straight position. With the hold-up tower shown in figure 7.4, we don't have the option of adjusting the elevation of the strand after it's been tensioned. Any adjustment to the elevation has to be done before the strand is tensioned. So figure 7.4 would typically be used for either tensioning the strands straight in the upper position or tensioning the strands in the draped position. All right, we can also push the strands down to the hold down locations after the strands have been tensioned. This is the typical procedure that's used when manufacturing draped strand double T's. If you look at figure 7.6 on page 7.6, this shows a cross section through a double T bed that is going to have draped strands. So again, we would tension the strands in the straight position, but then we need to have some method of pushing the strands down into the draped position. And so the way that we would do that is we would have a hold down reaction beam that spans across the bed at the hold down location. We have pins that go through the hold down beam that align with the strands, and then we use a hydraulic ram to push the depressor pins down, and as they go down, they collect the strands in a fork at the end of the depressor pin, and they push the strands down in the cross section. We then put a locking pin through the depressor pin and the hold down reaction beam, and that holds the strands in the draped position while we then cast our concrete. So for a closer look at that fork at the end of the depressor pin, you can flip over one page to 7.8. That's just a close-up of the fork that would be on the depressor pin that's shown in figure 7.6. And those strands would be stacked inside that fork as the depressor pin is pushed down and it encounters each strand in its straight position. It would collect those strands in that fork and then push those strands down as they stack on top of each other. So the way this works is the depressor pin holds the strands in the drape position while the concrete is being cast. After we've achieved initial stripping strength, we can then release the depressor pins, remove the hold down reaction beam, and pull those depressor pins out of the concrete. Generally, they're tapered so that they're larger at the top, larger in diameter at the top than the bottom. They're generally greased so that they come out of the hole, come out of the concrete easily, so that the depressor pin can be used multiple times. The only thing that is cast within the concrete and remains is the fork that's shown in figure 7.7b. So that remains in the concrete at the hold down location. Right, so that's the typical way of manufacturing drape strand double T's. Figure 7.7a is a hold down device that's oftentimes used in bridge girder production. for strands that are either tensioned in the draped position or they're tensioned in the lower position straight and then pulled up at hold up points. This hold down device is not movable after the strands have been tensioned. It is fixed in place. So you can see that the black dots represent the strand, and you can see that in the hold down device we have bevels in the pins. That helps to keep the strands properly aligned. It's faced horizontally from each other. Those pins that hold the strands down have bearings so that they are rollers. So as the strand is tensioned and elongated, those can turn and avoid the buildup of an excessive amount of friction at the hold down location. The threaded portion of this device goes down through the soffit of the beam. So you can see that double horizontal line there below the hold down device. That represents the soffit of the beam bed. So we have a threaded rod that goes below the bed and is anchored underneath the bed, and that's what resists that force that's trying to pull that hold down device up. So during detensioning, as the strands are detensioned at a certain point, as dictated by the detensioning sequence, the workers on the bed would take their torches, they would reach underneath the bed, and they would cut that threaded rod and essentially release that hold down device. And then the remaining portion of the threaded rod can be threaded out of the hold down device. The hold down device will remain in the cast concrete. The little hole where the threaded rod was is then packed with grout to seal it up. All right, figure 7.8 is just a representation of how you would go about deflecting the strands into the draped position after they've been tensioned in the straight position. So there's nothing specific about this other than we always want to start at the center of the bed and alternate from side to side, moving from the center. So when I'm at a plant doing an audit and they are tensioning draped strands in the straight position and then pushing them down into the draped position afterwards, I'm going to make sure that I hang around and watch both the jacking operation as well as the draping operation. And so long as they start at the center of the bed and they push the strands down into the draped position following a symmetrical pattern, then they've met the requirement. They may not follow the exact pattern shown in figure 7.8. They may not do it exactly as what I would do if I was doing it, but so long as they start at the center of the bed and they make an effort to alternate from side to side as they continue on with the harping process, then they're meeting the requirement and it is acceptable. Right, a couple of other things to keep in mind is that when we have drape strand pre-stressing, generally the hold-up points are outside of the concrete. Usually the hold-down points are inside the concrete, and so the hold-down device is cast within the concrete. It's only used once. But the hold-up devices are outside of the concrete. They're usually between the beams or between the last beam and the header. And so the hold-up points can be used multiple times. That hardware can be used multiple times. So we want to be careful that we properly inspect our hold-up locations after each use. Make sure that the elevation is correct and that the hardware is in good working order. Since it is exposed to the elements, if it's an outside bed, the hold-up hardware can corrode over time. And so as it corrodes, then the rollers may not work as well as they should. And so we want to keep an eye on those hold-up points, make sure that they're inspected, that they're in good working order, so that we don't have any safety issues, and also so that we don't have any tensioning tolerance issues. Another thing to keep in mind is that when strands are tensioned in the draped position, typically the strands are parallel to each other throughout the length of the bed. And so that means the geometry of the strands is the same from one strand to the next. For all the draped strands, the geometry is going to be the same. And so that means we only have to do, when we're calculating how much force is occurring at those hold up and hold down locations, We can do that for one strand and then just multiply by the number of strands, and we've calculated our total force. Whereas if the strands are not parallel, which would be the case if we have a draped strand double T, where the strands were tensioned initially straight, and then they were pushed down into the draped position. So they started out in the straight position where they were a couple of inches apart from each other, or some other nominal value. But they ended up, after they were draped, stacked on top of each other in that fork, and so they are not parallel to each other. At the ends of the bed, the strands are further apart from each other. At the center or the hold down location, they're actually stacked on top of each other. And so the geometry is a little bit different, and so we need to take that into consideration in our calculations, and we'll talk about that a little bit more once we get into an example calculation. All right, so let's talk a little bit about tolerances. So just as a reminder, the tensioning tolerances for pre-stressing, we have 3 questions that we have to ask in order to determine whether or not a strand has been tensioned within tolerance. The first question is, was the applied force within plus or minus 5% of the required force? Was the applied force within plus or minus 5% of the required force? All right, our second question is, was the net elongation within plus or minus 5% of the calculated elongation? All right, was the net elongation, the measured elongation, within plus or minus 5% of the calculated elongation? So both of those questions are usually pretty easy to answer. We can calculate that pretty easily and determine whether or not the force was within plus or minus 5% and the elongation was within plus or minus 5%. But the third question sometimes trips us up. This is the one that if we make an error in calculating tensioning tolerance, usually it's this third question that does us in. So the third question is the deviation in force combined with the deviation in elongation 5% or less? So the total deviation in force and the deviation in elongation has to be 5% or less. And so the easiest way to evaluate this third test is to use a number line. And so if we use our number line, we can plot our force and we can plot our elongation, and then we can visually see whether or not we're meeting that third requirement, that the deviation in force combined with the deviation in elongation is 5% or less. So say we've got a tensioning operation, and for the first strand, for whatever reason, we apply a force to the strand that is 3% over the target force. All right, so you can come up with any number of reasons why that may be done. But let's say that we, for whatever reason, we choose to tension the strand and we go 3% over on our force. So that means that our force would be right there at the plus 3% value. All right, when we measure the elongation for that strand, we measure an elongation that's 3% under the calculated elongation. So that would put us right here on our elongation. All right, so let's determine whether or not this strand was tensioned within tolerance. So first question, was the applied force within plus or minus 5% of the required force? Yes, we're at plus 3%, that's within plus or minus 5, so yes, the force was applied properly. Okay, second question, is the measured elongation within plus or minus 5% of the calculated elongation? Yes, we're at minus 3%, that's within plus or minus 5% of the calculated elongation. Okay, now our third question, is the deviation in force combined with the deviation in elongation 5% or less? Okay, so we've got 3% on our force, minus 3% on our elongation, And so what is the total combined deviation in force and deviation in elongation? All right, in this case, that would be 6%. Sorry, I'm drawing with the mouse, so it doesn't look the greatest, but that would be 6%. So in this case, that strand is out of tolerance. The combined error in force and error in elongation is 6%, which exceeds the allowable value of 5%. So that strand is tensioned out of tolerance. All right, let's do another example. Next strand, same tensioning operation. We're being consistent with our force, and so we are applying a force that's 3% over the required force, so that value is still good. We measure our elongation, and the elongation for our second strand is 2% over the calculated elongation. Okay, so force is 3% over, elongation is 2% over. So right here's our elongation. All right, so force was applied within 5%, elongation was within plus or minus 5%. So now let's ask our third question. Is the combined within 5%? So in this case, the combined error in force and elongation is only 1%. So yes, this strand was tensioned in tolerance. All right. So it's that third question that can sometimes mess us up, and using this number line is a great way to visualize that tolerance, answering that third question with regard to tolerance. And so that's what I would recommend that you do out on your scratch paper if you're doing a test, or if you're doing one of these in the plant, is out on the side of your tensioning report. Draw a little number line and then assess whether or not that strand was tensioned within tolerance. Okay, this is another table, another way of evaluating tensioning tolerance. I think the number line is easier, so we'll just skip that one. All right, next let's talk about stress strain curve, load versus elongation curve. This is something that you should have seen in level 2. So this is just intended to be a little refresher. So each shipment of pre-stressing strand that a plant receives should be accompanied with certification documentation. And one of the items in that package should be a stress strain curve, or sometimes called a load versus elongation curve. And it just shows the relationship between the stress in the strand and the strain. The stress is just the area divided by, is just the force divided by the area. So stress is directly related to the force in the strand. Strain is just the length of the strand divided by the strain. And so strain is directly related to elongation. So that's why we can also call this a load versus elongation curve as well. But notice that during the elastic range, that the relationship between stress and strain is a linear relationship. That means if you double the stress, you double the load, you double the elongation. If you take 25% of the load off, then you reduce the elongation by 25%. So there's that direct linear relationship between force and elongation. But at a certain point, you can put enough load on the strand that you no longer have a linear relationship between the force and elongation. Once you start approaching that point, that is referred to as the yield point, we're starting to damage the strand. So as long as we apply a force to the strand that's less than the yield point, then theoretically we can take the force off the strand and the strand will go back to its original length. And we can do that repeatedly. We're not damaging the strand. But once we get to the yield point, we have permanently elongated the strand, and the strand will not go back to its original length. It will go back some if we take the load off, but it will not go back to its original length because it has been permanently deformed. And then the further we move beyond the yield point, the more deformation occurs, such that with very little additional load, we get a significant amount of additional elongation. And so we refer to that range of force below the yield point as the elastic range, and beyond the yield point is the inelastic range. So in simplest terms, elastic range is good, inelastic range is bad. We want to stay out of that inelastic range. And in order to keep us out of that inelastic range, to keep us away from the yield point, the code, the building code, American Concrete Institute building code, actually prescribes a maximum force that can be applied to any strand. And that force is 80% of the breaking point of the strand. That's the maximum force that can be applied. The yield point is usually somewhere between 90 and 95% of the breaking strength of the strand. So by establishing the code limit at 80%, that's keeping us below the yield point, keeping us in that range where the relationship between load and elongation is linear, so we can accurately calculate the load based on the elongation or vice versa. All right, the material property that relates the stress to the strain, the load to the elongation, is the modulus of elasticity. So long as we're in that linear range, that material property that allows us to calculate the elongation based on the load is referred to as the modulus of elasticity. And for pre-stressing steel, the modulus of elasticity is usually somewhere in the neighborhood of 28 million psi. 28 million psi. All right, in your book, there's a good discussion of code limitations that apply to tensioning values and pre-stressing strand. That's on page 710 and 711. A lot of these limits are not really relevant to the plant. They're more relevant to the engineer designing the pre-stressed element. The key requirement that is relevant to the plant is that 80% limit as the maximum force that can be applied to the strand at any given time. And that's in that second paragraph on page 711, referencing that 80% limit. All right, so that's the maximum force that can be applied to the strand. We have a couple of different types of strand that you may encounter. We have what's called stress relief strand and low relaxation strand. So all strand that's domestically produced goes through a process, a stress relieving process that helps to reduce the amount of inherent stress in the strand that is developed due to the manufacturing process. So if you've never seen strand being manufactured, it's an interesting process. They take rods of steel that are then pulled through smaller and smaller dies to get the rod down to a wire that is the appropriate size to be wound into a strand. And so as the rod is being pulled through these dies to get it down to the size wire that's needed, there are certain inherent stresses that develop in the wire. Then once those wires, those 7 wires are taken and they're twisted into a strand, also you can get some buildup of stress in the strand as a result of that process. And so stress relieving process helps to relax some of that inherent stress out of the strand. So all domestically produced strand goes through a stress relieving process. Now, in addition to that stress relieving process, some strand can also be put through an additional stress relieving process that results in strand that is considered low relaxation. Okay, low relaxation strand is strand that will have a lower likelihood of relaxing under sustained load. So if you take a rubber band and you stretch it, and you hold it between your hands in that stretched position. If you held it for a long period of time, the rubber band would relax. It would apply less and less force to your hands. And obviously, we're not going to stand there that long for that to happen. But if we stretched a rubber band, say between two pins on a table that were held apart, and then over a period of time we went back and we kind of flicked that rubber band, we would find that over time it has less and less force in it because the rubber band is relaxing. Well, pre-stressing strands will do the same thing, not to the degree that a rubber band will, but they will relax. They will lose some of their force over time. By putting a strand through a low relaxation process, it helps to minimize the amount of force the strand will lose over time. So all strand is stress relieved if it's domestically produced, but only certain strand that's labeled as such is low relaxation strand. It's been put through this additional process to help to minimize the amount of relaxation that will occur after the strand has been stressed and is held in that stressed position by the concrete that surrounds it. All right, in level 2, we talk about losses that occur during the tensioning operation. We have dead end chuck seating losses. We have live end chuck seating losses. If we have a splice chuck in the setup, we have a loss associated with that splice chuck. You may have losses associated with bed shortening if it's a self-stressing bed. If it's an abutment type bed, you may have losses associated with abutment rotation. There are potential losses associated with changes in temperature. Again, if it is an abutment type bed, you may have temperature corrections. So all of those different losses and the corrections that we employ to help offset those losses apply to draped strands just like they apply to straight strands. Now, to help keep things a little more simple in level 3, we're not going to go back over all of those corrections that have to be applied in tensioning calculations. They do apply in the real world, but we're not going to complicate our calculations in level 3 by going through the corrections. All right, so just keep in mind that we're going to try to keep things more simple and not have to do that in level 3, but out in the real world, those same losses still occur and the corrections still need to be applied to the tensioning operation. So keep that in mind. Okay, reducing friction. There's some methods for reducing friction that are listed at the top of page 712. One of the things that we can do with draped strands to help make sure that we get the strands tensioned within the required tolerance is to tension the strands from both ends of the bed. Some DOTs require that draped strands be tensioned from both ends of the bed. So the way this would work is we would tension our draped strands at the live end like we normally do. We would make a note of the applied force and the measured elongation. And then we would take our jack down to the dead end of the bed and we would reapply our required force to each of the draped strands. And we would make a note of any additional elongation that we achieve. We would add those two elongations together. And so long as that cumulative elongation meets our tolerance requirements, then we can say the strand is tensioned within tolerance. So the same 3 tests apply. The force has to be within 5%, the elongation has to be within 5%, and the combined has to be within 5%. All right, so that's one of the things that we can do to help ensure that we have equal distribution of force along the length of the bed. Another thing is using the roller devices at hold ups and hold downs, as we've already discussed. We've also talked about depressing the strands symmetrically if they're tensioned initially in the straight position. Then when we go through our depressing sequence, we want to do that in a symmetrical pattern. Another way to ensure equal distribution of the force along the length of the strand would be to vibrate the strand. Now, I agree that in theory, this is true, but in practice, I've never seen it done that I can remember, and it's not something that I would necessarily recommend that a plant do. It's not something that I'm going to do personally, and if I'm not going to do it personally, then I'm not going to instruct somebody else to do it. But I agree that after the drape strands have been tensioned, if we go out there and start banging on the strand in the middle of the bed with a hammer to vibrate it, that may help to equalize the force in the strand. Or if we tap the strand with a concrete vibrator, that may help to equalize the force in the strand between the ends. But it just in practice doesn't sound like something that I would want to do or recommend that someone else do. And then lastly is vibration or lubrication. We want to keep those rollers lubricated at locations where it's not going to adversely affect the bonding of the strand to the concrete, such as at hold-up devices. We could even add external lubrication to the hold-up device so that the strand more easily moves across that location. So lubrication can certainly help to reduce friction as well. All right, with regard to detensioning, detensioning is a little bit more complicated when we have draped strands. Usually we're going to detension a portion of the bottom strands and then the drape strands and then return to the bottom strands. In what proportion we do that needs to be dictated by the design engineer. Usually when detensioning drape strand elements, such as bridge girders, because it is a little bit more complicated, usually we have a sheet of paper with the detensioning sequence shown that's given to each of the torch operators so that they can assure that they are detensioning the appropriate strand at the appropriate time, that they're cutting the hold down devices at the appropriate time as well. So detensioning is basically the same as straight strand, but with a little more complication in that we don't just need to make sure that the strands are detensioned simultaneously and symmetrically, but in addition to detensioning simultaneously and symmetrically, we need to make sure that we're detensioning bottom strands at the correct time versus drape strands, and that we're releasing the hold down devices at the right time as well. All right, so that's all the background on Chapter 7 and drape strand pre-stressing. Now we're going to jump into the calculations. The key thing that we have to be able to do in Chapter 7 in order to properly execute the calculations is we need to be able to calculate the diagonal length of a triangle. So thinking back to high school math, and the Pythagorean theorem, we know that the diagonal length of a triangle, C, is equal to the square root of a squared plus b squared. All right, so the diagonal length of a triangle, the C length, is equal to the square root of a squared plus b squared.
Steve?
All right, so yes.
Steve, you have a handful of questions if you want to tackle these before you get too far ahead.
Yeah, that's a good idea.
Okay, we have one. Why does the moment capacity for straight strand have a bit of a slope at the ends of the beam?
Yep, that's a good question. We don't get full moment capacity until the strand is fully developed. And so that little slope at the end of the diagram is just to represent that as the strand gets developed, it has more and more capacity. And then once it's fully developed, then we have a consistent and level capacity. So good eye. That's why there's a little bit of a slope right at the end of the beam. That's the development length of the strand.
All right, and then why not place strands at desired hold up or hold down locations instead of having to drape up or down?
Certainly can do that. That is one of the methods that we have available to us in tensioning. The reason that some plants don't do that is because the bed is long enough, they have enough beams in the bed that if they tension the strand in the draped position for 3 or 4 beams, due to the friction that builds up at each of those hold up and hold down locations, they would have a very difficult time getting the strands tensioned in tolerance, which means that they would then have to go to the end of the bed, the dead end of the bed, retension all of their draped strands in order to get them into tolerance. And so instead of going through all of that process, they found it easier just to tension in the straight position and then to push the strands down into the draped position. So it really just depends on how the bed is set up as to which method is most economical.
All right, and then we have, what is a soffit of a bed?
The soffit is the bottom of the form. So for a bridge girder, the soffit of the form would be the fixed portion that essentially forms the bottom of the beam. That would be the soffit.
All right, and then the last one we got was, when you stress from both ends, are you doing half the force on live end and half the force on dead end, or are you going all the way on both ends?
You're going all the way on both ends. Since the ends are connected with each other, in a perfect world, whatever force you put on one end is going to be the force at the other. But the reason we tension from both ends in some instances is because we know we've had some force lost between those ends. And so it is the same force that's applied at both locations, and it is the full tensioning force that's required for the strand.
All right, that is all the ones that came in.
Okay. All right, well, we'll jump into the calculations here. And as I go along in the calculations, I'll try to remember to stop after each example to see if there are any questions with regard to that example. All right, so the key calculation for drape strand pre-stressing that Chapter 7 hinges on is this calculation of the diagonal length C. So we're going to be doing a couple of different things once we've calculated our diagonal length. We've got 2 basic things that we're calculating in Chapter 7. The examples in the book kind of bounce back and forth between these 2 things, which is good in the sense that you get accustomed to doing both calculations, but it's bad in the sense that it's as you're starting this, it's hard to see that there are 2 distinctly separate things that we're doing because we keep bouncing back and forth between the 2. So here on the front end, before we get into any of the examples, I'm going to talk about what these 2 calculations are, and that really it's the C value that is common to both. But beyond that, there really is no connection between these 2 different calculations we're going to do. So the first calculation that we're going to do is we're going to calculate the vertical force that occurs at our hold up and our hold down locations. So if you just think about these hold up devices and hold down devices, as the strand changes direction, as it goes from horizontal to a diagonal, there's going to be a vertical force that occurs at these locations. And so we need to be able to calculate what that vertical force is so that we can make sure that our hold up and hold down devices have adequate capacity, and also so that we can make sure that whatever our hold up and hold down devices are connected to have adequate capacity. So generally a bed has to be reinforced underneath to resist the load, that vertical force that results from hold down locations. And then at our hold up devices, whether we're using a column or we're using a portal frame as our hold up device, that assembly has to be capable of resisting that vertical load that is generated at that hold up location. So that's one of the things that we're going to calculate. One of the 2 things that we're going to calculate in Chapter 7 is what is that vertical force at the hold up and the hold down location. All right. The other thing that we're going to calculate in Chapter 7 is we know that when we tension the strand in the straight position and then we push it down or pull it up into the draped position, that we're elongating the strand and we're adding force to the strand, we need to be able to calculate how much force is being added to the strand so that we can accurately determine what our jacking force should be. So again, the example I used earlier, if we have a strand that the engineer has specified, it needs to have 30,000 pounds of force in it when everything is said and done, but we're tensioning that strand in the straight position and afterward pushing it down into the draped position. And we know that when we push it down into the draped position, it's going to gain 6,000 pounds of force. Then that means we need to tension the strand with our jack to only 24,000 pounds. So we're going to tension the strand straight to 24,000 pounds. Then we're going to push it down into the draped position. It's going to gain 6,000 pounds when we do that, so that once everything is complete, the strand has 30,000 pounds of force in it. Okay, so that's the second calculation we're going to do. We're going to determine how much force is gained when we go from the straight to the draped position. And we're going to need to know C, the diagonal length, in order to calculate that. All right, so C is common to both of those calculations, but beyond that, those two calculations are not related to each other. So the vertical force at my hold up and my hold down location has nothing to do with the amount of force that the strand is going to gain when I go from the straight position to the draped position. Okay, I'm going to calculate those two things, both of them using C, but beyond that, there's no relationship between that vertical force at my hold up and hold down locations and the increase in force in the strand when I go from straight to draped. Okay, so those are two separate calculations, and as long as you can kind of keep straight in your mind that those are two separate things, then you won't have any problem with Chapter 7. One of those things is very easy to calculate. We're going to look at that on the next slide. The other one is a little bit more complicated, but it's the steps are pretty basic, and as long as you understand those steps, it's not complicated. So if you can keep those two calculations separate in your mind, then you won't have any issues with the tensioning calculations on the exam or applying what you're learning in Level 3 out at a plant. All right. So before we get to that first calculation operation, just a quick review. Our basic elongation from Level 2 is P times L over A times E. The P is the force in the strand, L is the length of the strand from chuck to chuck, A is the area of the strand, and E is the modulus of elasticity. Now typically the area and the modulus of elasticity are going to be givens. We're also going to be given how much force is required to be in the strand, and we should be given a diagram that shows us what the length of the strand is from chuck to chuck. So P, L, A, and E should all be given to us, and so we can calculate our basic elongation as P times L over A times E. All right, so now let's talk about the vertical force at the hold up and the hold down locations. So looking at our triangle, we got A is the horizontal length of our triangle, B is the vertical leg, and then C is the diagonal. So applying this to a draped strand, A would be the horizontal length of the strand between the hold up location and the hold down location. B would be the vertical offset of the strand between the hold up elevation and the hold down elevation. And then C would be the actual diagonal length of the strand between the hold up and the hold down. All right, so given that geometric relationship, if our force in our strand is P, and after the strand is in the draped position, that means that the diagonal portion of the strand has a force of P, we can then calculate what the horizontal and the vertical force would be based on our geometry. And so what we find is that the vertical force is related to the diagonal force the same as B is related to C. So the vertical force is equal to P times B divided by C. That is the vertical force at our hold down device and at our hold up device. P times B over C. Now in your book at the top of page 713, it has that vector diagram showing P as your diagonal force and that the vertical force is P times B over C. And then you have equation 7.3 that the vertical force is P times B over C. And then there's a note under equation 7.3 on page 713. And that note says that we can approximate the vertical force by substituting A for C. So we can approximate the vertical force as P times B over A. All right, that is true. We can approximate that vertical force as P times B over A, but we're not going to do that. There's no point in approximating what that vertical force is when we can very easily calculate exactly what that vertical force is. Okay, so that note is correct. We can approximate the vertical force as P times B over A, but that's not a good idea because in some instances, the geometry is such that the approximation is very close to the exact value. But in other instances, the geometry is such that there's more error between the approximation and the exact value. So because there can be some variation there, we're not going to approximate, we're going to use the exact calculation, P times B over C. So in the book, they use the approximation, but we're going to do the same examples on our slides, and we're going to use the exact calculation. And that way you can see the difference between the slide and in your book between the exact value and the approximate value. But matter of fact, in the new version of TM 103, they've taken out this little blurb about approximating the vertical force. They've just gotten rid of that altogether, and they do all of the examples calculating the vertical force exact using P times B over C. All right, so let's look at a little application of this. So we've got a bed. This is 7.6.2. We've got a hold up location, and we've got two hold down locations at the center of each of the two beams in the setup. And so the vertical force at the hold down location is going to be P times B over C. That that's the final force in the strand after everything's said and done. If the engineer said we need to have 30,000 pounds in the strand and we've done everything correctly, we end up with 30,000 pounds in the strand, then our hold down force would be 30,000 pounds times B divided by C. All right, for our hold up device, the geometry is the same, A is the same, B is the same, C is the same. So our hold up number one, the vertical force is P times B over C. Okay, let's look at hold up number two. Hold up number two is a little bit different than hold up number one. It's different in that there are two diagonals coming in to hold up number two. All right, so what that means is that we have a vertical force associated with each of those diagonals. So the force at hold up number two is going to be 2 times P times B over C. Okay, we have two diagonals coming into that point, and so the total hold up force there is going to be twice as much, 2 times P times B over C. All right, let's look at another one that uses the vertical force. So here's 7.6.3. So in this case, we've got a single point hold down at the center of each of the two beams in the setup. And so our hold down force, we have two diagonals coming into that hold down location. So the force is 2 times P times B over C. 2 times P times B over C. Now looking at our hold up locations, we've got one diagonal that comes into the hold up location. And so that means the vertical force at the hold up is P times B over C. All right, so that's how we go about calculating the vertical force at the hold up and the hold down location. So I'm going to pause right there to see if anybody has any questions.
No questions have come in.
All right. Okay, so that's one thing that we're going to be calculating in Chapter 7, the vertical force at the hold up and the hold down locations. All right, so that pretty straightforward. P times B over C. If you've got two diagonals, it's 2 times P times B over C. All you have to do is calculate your C. A and B are given. Pretty easy to calculate that vertical force. Okay, let's look at the second calculation for Chapter 7. Second and final calculation. All right, in this calculation, we're going to determine how much force the strand gains when it goes from the straight to the draped position. Okay, how much force does the strand gain when it goes from the straight to the draped position? All right, so we've got a 5-step process here. And so I want to encourage you to focus on the 5-step process and not focus on the numbers. Because the numbers you can come up with an infinite variety of example problems that use different numbers, but you would solve all of those problems the same way, which is this 5-step process. All right, so sometimes when I'm teaching this class in person, we go through these example problems on the overheads, and then we talk through some of the example problems in the back of the book. And then people are still asking for more example problems. And usually when that is the case, I know that we have a problem because they're focusing more on the numbers as opposed to the process for solving the problem. If you're focused on the process for solving the problem, then you're not worried about how many example problems or what the numbers are because it doesn't matter. The solution is the same process for all of them. Okay, so focus on these 5 steps and how they're applied in these example problems. Apply these same 5 steps to the problems that you work from the back of the book and then in the supplementary questions. And as long as you have an understanding of what each of these 5 steps is doing, then you should be good to be out in a plant, given a setup, and you need to do some calculations to prepare for a tensioning operation. You should be good to go. For the exam, you should be good to go if you understand these 5 steps. Okay, so focus on the steps, not on the numbers. So step number 1 is calculate the basic elongation. All right, so again, P times L and A times E, all of those numbers should either be explicitly given to us or shown in a diagram. And so it's just plugging in the numbers and calculating our basic elongation. Okay, the most difficult part of calculating the basic elongation is making sure that all of our units are consistent. Okay, we can't mix up feet and inches. We can't combine bed length in feet with area in square inches. Okay, we have to have our bed length in inches so that it matches up with our area in square inches. We can't have our force in kips and then our modulus of elasticity in pounds per square inch. We need to be consistent in both our force unit and our length unit. But as long as you are consistent in your units, our basic elongation is P times L over A times E. So in this example up on the screen, we're given a required force of 28.91 kips. We've got a strand length, chuck to chuck, 206 feet. We're given an area of 0.153 and a modulus of elasticity of 28,900 KSI. All right, so to get everything in the same units, we're going to multiply our bed length by 12 so that we've got consistent inches in the numerator and the denominator. We've got our force in kips. We've got our modulus of elasticity in kips per square inch. So we've got consistency in our force units. And so that gives us a basic elongation of 16.16 inches. All right, next let's calculate our diagonal length C. So A is 30 feet, B is 5 feet, so C is the square root of A squared plus B squared. So in this case, C is 30.41 feet. 30.41 feet. All right, step 3, let's determine how much this strand is going to elongate when we go from the straight position to the draped position. All right, so our elongation for each diagonal is just the difference between C and A. So in this case, A is 30 feet, C is 30.41 feet. So that means that this strand is elongating 0.41 feet for each diagonal. Okay, we have two diagonals. So our total elongation is going to be 0.41 feet times 2 times 12. We've got two diagonals, so we're going to multiply by 2, and we're multiplying by 12 to get our elongation into inches as opposed to feet. Typically, we measure elongation in inches, so we're just converting from feet to inches. All right, so now we know that when we go from the straight to the draped position, this strand is going to gain 9.84 inches of elongation. That's all well and good, but we want to know how much force the strand gains. So we can calculate the force based on the elongation. In level 2, we were typically calculating the elongation based on the force, but now we're calculating the force based on the elongation. So we're just going the other direction. All right, we've already calculated that we get 16.16 inches of elongation for an applied force of 28.91 kips. So we can set up a ratio to determine how much force we get from 9.84 inches of elongation. So this next slide shows us that. So our added force divided by our added elongation is proportionally equal to our applied force divided by our elongation. Okay, so PA is the force that's gained when we go from the straight to the draped position. Delta A is the added length when going from the straight to the draped position. P is the force used to calculate our basic elongation, and then delta is just our basic elongation. Okay, we already know P, delta, and delta A, so we can solve for PA, the force that's gained when we go from the straight to the draped position. So we're going to take that ratio, we're going to rearrange it to solve for the added force, P sub A, and we get that P sub A is equal to the added elongation times the target force divided by the basic elongation. All right, so that's our calculation. So let's go back to step 4 here. And so we're just going to plug in our added force is equal to our added elongation times our required force divided by our basic elongation. That gives us 17.60 kips. So we know we're going to gain 17.6 kips when we go from the straight to the draped position. So we need to deduct that 17.6 kips from our jacking force. So we're going to tension our strand in the straight position to 11.31 kips. We're then going to gain 17.6 kips going from straight to draped so that we end up with 28.91 kips of force in the strand once everything is said and done, which is the target force that the engineer specified. All right, so let's take some questions from this one. So this is the second calculation that we're going to do in Chapter 7. And it's, again, this 5-step process. You don't have to always do the 5 steps in this order. You can calculate your C before you calculate your basic elongation. That's fine to do that. You can calculate your added elongation before you calculate your basic elongation. Some of these don't have to be done before the others, so long as you do the 5 steps. Okay, so any questions on this before we get into some more example problems?
We have 2 questions that came in. Our first one is, in 7.6.2, is it possible to have the 2 diagonals that hold up 2 to have different slopes resulting in different force?
It is possible. That rarely occurs, but it is possible. You could be casting 2 bridge girders that have differing lengths, and if they have differing lengths, then those 2 diagonals would have slightly different geometry. So it would be possible that you would have to calculate P times B over C for each of those 2 diagonals and then add those 2 values together. But as long as the geometry is the same, then the vertical force is the same for those 2 diagonals, and it's just 2 times P times B over C.
All right, and then we have someone who asked, on the previous slide, could you highlight the triangle?
Highlight the triangle. So on this slide,
Let's see if he tells me. Yes.
okay. So A is your horizontal length. So right there is your A. B is your vertical length. So here would be your A. Again, not a straight line, sorry. B would be right here. And so then C would be here. So that's your triangle. And so long as A and B are the same, then that means all of your diagonals are the same. So in this setup, by all indications, A and B is the same for all 4 diagonals. So the C for all 4 of these diagonals would be the same C. Did that answer the question?
Yes.
Okay, great. Any other questions at this point?
That is it so far.
All right. Let's look at another example. All right, in 7.7.1, we've got a beam with parallel depressed strands. So these are strands that are tensioned in the draped position. And so we're going to be looking at the vertical force at our hold up and our hold down. Okay, so first thing we're going to do here is calculate C. C is square root of A squared plus B squared. So A is 20 feet. B is 1.5 feet. So that gives us a diagonal length C of 20.06 feet. We don't really need it, but they're calculating it here anyway. The added length per diagonal is 0.06 feet. Again, we don't need that for the vertical force, but they went ahead and showed that calculation anyway. So the length of our strand from chuck to chuck would be 50 feet plus that added length for our diagonal. We've got 2 diagonals. So our overall length would be 50.12 feet. So again, for the vertical force, we don't necessarily need that, but they're showing the calculation anyway, so that's fine. So let's look at our vertical force. So our hold-up force is P times B over C. So the required force in the strand is 29,000 pounds. B is 1.5 feet. C is 20.06 feet. And so when we calculate that out, we get a vertical force at our holdup of 2.168 kips per strand. 2.168 kips per strand. All right, 2.168 kips per strand. All right, let's look at our hold down. Okay, at our hold down, we have two diagonals coming into that point. The geometry is the same, the diagonals are the same. So that means that our vertical force is going to be 2 times P times B over C. We've already calculated P times B over C is 2.168 kips. So that means the hold down force is 4.34 kips. It's twice as much as the hold up force. That's 4.34 kips per strand. All right. Any questions on that one?
No questions.
Okay. So if you look in your book on page 7.17, in your book, they did this same example, but they approximated the vertical force, whereas we calculated it exact. So they got 2.175 and 4.35, whereas we got 2.168 and 4.34. So you can see in this instance, the approximation was pretty close. Pretty close. That's within a round off error probably. They're pretty close, within one value of the third decimal point. So in this example, the approximation's pretty close. In other examples, it may not be so close. So always calculate exact. All right, let's look at another example. All right, in this case, 7.7.2, we are tensioning in the straight position, and then we are pushing down into our draped position. And so we need to know how much force we're going to gain when we go from the straight position to the draped position. All right, so one thing that we need to do is we need to calculate our diagonal length C. So C is equal to the square root of A squared plus B squared. And so we get a C length of 300.426 inches. All right, the added elongation is the difference between C and A. So C minus A is 0.426 inches. We have 8 diagonals. So our total added elongation is going to be 8 times 0.426 inches for a total added elongation of 3.41 inches. All right, so we've already done 2 of our steps. Our third step is to calculate our basic elongation, P times L over A times E. P is given. L is shown in our diagram. A and E are given. And so we can calculate that our basic elongation is 15.86 inches. All right, 15.86 inches. All right, so that is our added elongation. That is our basic elongation. And so now we can use those two to calculate, to set up our ratio to calculate our added force. So remember, our added force is equal to our added elongation times our required force, in this case 28,920 pounds, divided by our basic elongation, 15.86. And so we get that when we go from the straight to the draped position, we're going to add 6,200 pounds in this setup. All right, so if our target force is 28,920 pounds, and we know we're going to gain 6,200 pounds going from straight to draped, then that means that we need to tension the strands in the straight position to 22,720 pounds. All right, any questions on that one? So again, it's the same 5 steps that we looked at on the previous slide. We didn't necessarily do them in the same order, but it's still the same 5 steps.
Someone said, can you clarify the lengths along the top? I'm not sure what that means.
Yes, this graphic, something happened in translation. It's not as clear as the graphic in your book on page 717. But that 50 feet is from the chuck to the first holdup, 50 feet from there to there, 50 feet from there to there, 50 feet from this holdup to the end of the bed. So a total of 200 feet. So it's more clear, shown more clearly on page 7.17.
Okay, that's the only question.
Okay.
One more, sorry. Do we
All right.
need to consider the force and elongation corrections?
Yes. In the real world, when you're going through this process, you will have to consider corrections for live end seating, dead end seating, bed shortening, abutment rotation, temperature corrections. All of those would apply as well. Again, we're trying to focus on the drape strand calculation, so we're trying to keep it as simple as we can in the book by not bringing those other things into the process, but in the real world, they are there, and you would have to consider those.
Okay. There we go. You guys are all set.
All right. Let's look at 7.7.3, the last example in the book. So in this case, we've got a double T bed that's shown, the cross section and the draping is shown on page 719. So we've got a double T bed that's going to be tensioned in the straight position and then pushed down into the draped position. And so the question is, what is the vertical hold up and hold down forces? All right, so a little clarification on the diagram. So you can see there that at the end of the bed, the strands are numbered and they're spaced out, and the spacings are shown B1, B2, B3, B4, B5. And then those spacings are given there in the middle of the page. B1 is 2 inches, B2 is 8 inches, so on. But look at the hold down location. The hold down location is shown more accurately in section AA. And so section AA shows that the strands are stacked on top of each other at the hold down location. So this is what we were talking about a little bit earlier. We've got that fork on the end of our depressor pin. And as that depressor pin is pushed down, that fork collects the strands so that where the strands are separated from each other at the end of the bed, at the hold down location, they're stacked on top of each other. So essentially they're a 1/2 inch apart. These are 1/2 inch diameter strands. And so each strand center to center is a 1/2 inch apart, as shown in section 8A. All right. So I wanted to go ahead and clarify that because once we get into these calculations, I oftentimes get the question of where did that B value come from? And so if you look at the spacing of the strands at the end, and then you look at the spacing of the strands at the hold down, they're a 1/2 inch apart at the hold down, then you can accurately calculate what the B dimension is between the hold up location and the hold down location for each strand. All right, so let's calculate that hold up force. All right, so for strand one is not draped. The elevation at the end and at the hold down is the same, so there is no vertical force for hold up one due to strand one. All right, let's look at strand two. So for strand two, B is 5.5 inches. So again, it's at the end of the bed, it's at 8 inches, which is 2 inches above strand one. But then at the hold down location, it's a 1/2 inch above strand one. And so that gives us a total B of 5.5 inches for strand two. So we calculate C, square root of A squared plus B squared. Then we can calculate our vertical force as P times B over C. So 31 kips times 5.5 divided by 360.04 gives us a vertical force of 0.47 kips for strand two. All right, for strand three, we have a B of 9 inches. C is 360.11 inches. And so our hold up force is 0.78 inches. All right, for strand four, B is 12.5 inches. C is 360.22 inches. And so when we plug into P times B over C, we get a vertical force of 1.08 kips. And then for strand five, B is 16 inches. C is 360.36. And the vertical force is 1.38 kips. Okay, so the total hold-up force is all four of these strands combined, so that would be 3.71 kips. Hold-up number two, and at the hold-down location, we have two diagonals for each strand, so the force is twice as much. So at hold-up number two and hold-down, and at the hold-down locations, we have a vertical force of 7.42 kips. All right, so this one looks a little complicated because there's so many calculations going on. But notice that the calculations we're doing for each strand, it's the same calculation. It's C equals A squared plus B, square root of A squared plus B squared, and the hold-up force is equal to P times B over C. Okay, we're having to do this for each strand separately because the geometry of each strand is slightly different. But the actual calculation is the same equation. So I just don't want you guys looking at this and thinking, wow, you know, this is really complicated. It's not. It's C equals the square root of A squared plus B squared, and the hold-up force is P times B over C. That's all it is. It's just you're having to do those calculations for every strand because the geometry of each strand is slightly different. All right, so don't let the repeated calculation make it appear more complicated than it actually is. All right, so that's the last example in chapter 7. So we've got some time left. What kind of questions do you guys have on chapter 7? Hopefully, while you're thinking about questions and typing them in, hopefully going through this together has clarified some things. Hopefully it's simplified some things. Keep in mind that there are just two basic things that we're calculating in this chapter. One is the vertical force, P times B over C, and then the other is the force that the strand gains when it goes from straight to draped, and that's that 5-step process. Those two calculations don't have anything to do with each other than that they both use C. They're both related to the geometry, but beyond that, they're two independent calculations. All right.
We have 3 questions that came in. The first one was, how did we get B in this example?
Okay. So for strand number 2, at the end of the bed, we're given that it's at an elevation of 8 inches. At the hold down location, it's at an elevation of 2.5 inches. And so the net vertical deviation is 5.5 inches. Same process for strand number 3. At the end of the bed, we're given that it's at 12 inches. But at the hold down location, if you look at section AA, you can see that it's at 3 inches. It's a 1/2 inch above strand number 2 because they're a 1/2 inch apart. And so that means that the actual vertical offset B for strand 3 is 9 inches. So on and so forth. So you just have to look at that section AA, look at the B that's given for the end of the bed, and then look at the section AA, and the difference between the strand location between those two is the actual vertical offset.
You may have just answered your next question, but I'm going to say it anyway. Where is the number 2.5, etc., coming from on line B2?
Yep, so that's coming from section AA. If you look at section AA, you can see that strand 1 is at 2 inches, and then each subsequent strand is a 1/2 inch above the previous strand.
All right, and then the last question we've gotten, so 2 more. The next question we have is on the handout, it says 5 double T's. Is that then multiplied by 5?
5 double T's. I'm not sure what they're referring to with 5 double T's.
7.73, he said.
7.73. Okay, it looks like there's 5 beams in the bed. It doesn't really matter how many beams are in the bed because we're looking at the vertical force at the hold up and the hold down location. So it doesn't matter how many beams are in the bed. We're only looking at the vertical force at the hold up and the hold down locations.
All right, and then we had, am I correct in interpreting that the harped strands will always need to be straightened near the ends of the beds, and so there needs to be hold up or hold down near the end of the bed?
Generally, that is correct. I have seen tensioning setups where the strand came into the abutment at an angle, and then there was a stressing plate that was at an angle so that the strands were actually tensioned. The jack was at an angle, tensioning the strand as opposed to being horizontal. So I have seen that done. That is very unusual. Most of the time, you are correct. There would be a hold up at near the end of the bed so that the strand is horizontal at the chuck.
All right, those are the only questions that have come in.
Okay. Well, I'll talk for just a second. So if there's anybody typing, you've got time to finish your question, or if you come up with a question, you've got a little bit of time to type it in. But that wraps up today. But tomorrow, we're only covering chapters 8 and 9, so that will not take the full 4 hours that is allotted. It won't take anywhere near the full 4 hours. So usually what we do on the fourth day is we start things off by seeing if there are any questions from the previous day. If you're typing right now, keep typing and we'll get your question addressed. But as you look over this information later on today, as you're studying tonight, if a question comes to you, then have that question ready. And when you get online tomorrow afternoon, before Lauren gets things going, go ahead and type in your question, and then Chance will start tomorrow by answering any questions that you may have that may have come up between now and then. It doesn't have to be Chapter 7 only. Anything that we've covered, if you've got a question, then feel free to put that in, and we've got plenty of time tomorrow to field whatever questions that you've got before we get things going with Chapter 8. And then during the session tomorrow, if you come up with questions, then be typing those in, because we'll have time after Chance finishes Chapter 9 to address those as well. So if there's any more questions now, be glad to answer those. If you don't have any at the moment, there should be plenty of opportunity tomorrow to ask any questions that may come up in the interim.
One more question did come in.
Okay.
He wrote, does the hold-up force go and stay into the precast concrete element when the strands are released and the element is stripped from the bed?
It does, in the sense that the strands are now surrounded by concrete. So it's the concrete that is resisting that vertical force and not the hold down or the hold up in the bed anymore. So yes, that vertical force is still present. It's just being resisted by the concrete in the precast unit.
Okay, it looks like that's the last question for you. There was one question that came in for me, but it's probably beneficial for everybody. They asked if the classes are being recorded. They are being recorded. I will be sending them either tomorrow night or Friday morning, depending how quickly all the recordings convert. And it doesn't look like anybody else is typing anything, so we can go ahead and wrap up. Oh,
Okay,
hold
great.
on, one more just came in. Are the hold-up columns on the outside of the bed?
Usually they're sitting on the soffit of the bed. They're sitting on the same surface that casts the bottom of the beam. It's just that they're sitting between beams, so they're not cast in concrete. There is the other option, the portal frame that was shown in, and so figure 7.4, that column would be sitting on the soffit of the bed. It's just sitting between beams, so it's not cast in concrete. Figure 7.5, that hold-up device, those portal columns are outside of the soffit of the bed. They're on either side of the soffit of the bed. So hopefully that answers the question.
I'm going to assume that was the last one. So I'm going to go ahead and start wrapping up. All right. Okay. Thank you for attending this session. Certificates of continuing education will appear on your account at www.rcup.net within 10 days. I did enter today's during the class, so you should also have day 1, day 2, day 3 so far. Remember that continuing education credit is given for each individual session. If you have any questions at all, please go ahead and email me at lbell@pci.org. You will receive an email from our certification team. I'm pretty sure that they said they sent that already, so you should have that in your inbox. And then this concludes this session. Thank you for attending and have a great evening.
Thanks, everyone.